Hello there and welcome to Physics with William, where we take some of the biggest ideas in physics, slow them down, and give ourselves enough time to understand what is actually going on. Tonight we are going to look at something that sounds as though it should be obvious from its name, but becomes much stranger the closer we examine it. It is called the strong interaction, more commonly known as the strong force, and it is the strongest of the fundamental interactions known to physics. That might sound surprising because when most of us imagine a powerful force, we tend to think about gravity. Gravity holds us to the surface of Earth, keeps the moon in orbit, holds planets around stars, and helps shape galaxies containing billions of suns. It seems difficult to imagine anything stronger than a force capable of organizing objects on such enormous scales. Yet if we shrink our attention from planets and stars to the interior of matter, gravity becomes almost irrelevant. Down there, inside protons, neutrons, and atomic nuclei, another interaction dominates so completely that gravity barely enters the discussion. The strongest force in the universe does not throw planets around or drag stars into black holes. Most of the time, it works in spaces far smaller than an atom, quietly holding together the particles from which ordinary matter is built. Before we get too far into that tiny world, I would love to know where you are listening from tonight. Perhaps it is late where you are and the room has finally become quiet. Perhaps your day is only beginning, or maybe you are somewhere in between, listening while working, resting, travelling, or trying to convince yourself that one more science video is definitely part of a sensible bedtime routine. Wherever you happen to be, take a moment to look at the nearest solid object. It could be your phone, a table, a wall, a pillow, a cup, or perhaps something less convenient like a cat that has decided your arm is now furniture. Whatever you are looking at, it is made from atoms. Inside those atoms are nuclei. Inside most of those nuclei are protons and neutrons. Inside the protons and neutrons are quarks, and those quarks remain bound together because of the strong interaction. So although this force operates at distances we cannot directly see, almost everything familiar around you depends on it at some level. If you enjoy these quiet journeys through physics, you're very welcome to like the video and subscribe to the channel. It helps other curious listeners find this little corner of science, and it means we can continue taking subjects that sound intimidating at first, and discovering that they become much friendlier once nobody is rushing through them. The first thing to understand is that physics currently describes nature using 4 fundamental interactions. Gravity is one, electromagnetism is another. Then there is the weak interaction, followed by the strong interaction. Each of these plays a different role, and the word fundamental means that, as far as our current theories tell us, these interactions are not simply ordinary forces made from something more basic underneath. Gravity shapes the large-scale structure of the universe. Electromagnetism controls electricity, magnetism, light, chemistry, and much of the behaviour we encounter in everyday matter. The weak interaction is involved in certain kinds of radioactive decay and in important processes inside stars. The strong interaction works mainly in the subatomic world. If we judge these interactions only by how strongly individual particles affect one another at the scales where the comparison makes sense, gravity comes out remarkably weak, while the strong interaction sits at the other end of the scale. This can feel completely backward, because gravity is the interaction we experience most obviously. Drop a book and gravity pulls it toward the floor, jump into the air, and gravity brings you back. Nobody has ever misplaced their keys, because the strong interaction suddenly dragged them underneath the sofa. The reason is not that the strong interaction lacks power, it is that its direct influence is confined to extremely small distances. Range changes everything. Gravity is weak at the particle level, but it has effectively unlimited reach, and it is always attractive between ordinary masses. Every piece of matter contributes to it. Put enough matter together and those tiny gravitational effects add up until they can control moons, planets, stars, galaxies, and clusters of galaxies. The strong interaction behaves very differently. Its most obvious effects are restricted to the scale of atomic nuclei and smaller structures. Once you move outside that tiny region, the direct strong interaction does not continue reaching outward in the way gravity or electromagnetism can. This means you can sit beside another person without the quarks in your body strongly binding themselves to the quarks in theirs, which is fortunate for several social and practical reasons. At ordinary distances, the strong interaction is hidden, because the particles it acts on are already locked inside larger structures. We experience the consequences of those structures rather than feeling the interaction itself. It is a little like having extremely powerful machinery sealed behind the walls of a building. The machinery may be essential to keeping everything running, but from the hallway all you notice is that the lights stay on. To see why nature needs such a powerful interaction, we can begin with the atomic nucleus. At the centre of an atom is a nucleus containing protons and, in most atoms, neutrons. Protons have positive electric charge. Two positive electric charges repel each other because of electromagnetism. This creates an immediate problem. Many atomic nuclei contain several protons packed very close together, and according to electromagnetic behaviour alone, those protons should be trying to push one another apart. The more protons we add, the more serious that repulsion becomes. Gravity cannot rescue the nucleus, because at this scale, gravity is far too weak. Something else must provide enough attraction to keep nuclear matter together when the particles are close enough. The strong interaction is the underlying reason that this is possible. More precisely, the force binding protons and neutrons inside nuclei is a residual effect of the deeper strong interaction acting inside those particles. We will get to that distinction gradually because it becomes important later. For the moment, the important point is that without strong interaction, physics, the nuclei of most chemical elements could not exist in their familiar form. Think about what that would mean. Carbon depends on a nucleus containing several protons and neutrons. Oxygen does as well. So do nitrogen, calcium, iron, silicon, gold, uranium, and nearly every other element beyond the simplest form of hydrogen. Chemistry depends on atoms having particular nuclei, because the number of protons determines which element an atom is. Change the nuclear structure and you change the atom. Without stable nuclei, there would be no ordinary periodic table, and without that familiar collection of elements, there would be no familiar chemistry. Water would not exist in the form we know. Rocks would not have their present composition. Biological molecules would not be available to build cells. Stars would not process nuclear fuel in the same way. The world would be so different that describing it as merely strange would be rather generous. The strong interaction, therefore, does not need to reach across the room to matter to us. Its influence was already built into the material of the room long before we arrived. The deeper surprise came when physicists discovered that protons and neutrons themselves were not fundamental. For a period of time, it was reasonable to treat the proton and neutron as basic building blocks. They were small, they lived in nuclei, and there seemed to be no obvious reason to expect another level beneath them. Experiments eventually showed otherwise. When researchers fired high-energy particles into protons and examined the scattering patterns, the results suggested that protons contained smaller components. Those components are quarks. A proton contains 3 main quarks that determine its basic identity, and a neutron also contains 3 main quarks arranged differently. Saying that there are 3 quarks, however, should not make us imagine 3 tiny balls sitting quietly inside a larger ball. The interior of a proton is a highly active quantum system. Quarks interact with fields. Gluons are constantly involved. Additional quark and antiquark activity contributes to the internal structure. Energy and momentum are distributed in ways that do not resemble a miniature mechanical clock. If you opened a proton, expecting to find 3 neatly labelled compartments, quantum physics would disappoint you almost immediately. The strong interaction acts directly on quarks, and the particles associated with carrying this interaction are called gluons. The name comes from the idea that they help glue quarks together, although physical glue would be a dangerously simple picture to take too literally. Gluons are elementary particles in the modern theory of the strong interaction, which is called quantum chromodynamics. Quarks interact through gluon fields, and these interactions are responsible for keeping quarks confined inside particles such as protons and neutrons. One important difference between the strong interaction and electromagnetism is that the carriers of the strong interaction can interact with one another. Photons, which carry the electromagnetic interaction, do not themselves possess electric charge. Gluons, by contrast, participate in the strong interaction they help transmit. This single difference leads to a great deal of the unusual behaviour we associate with strong interaction physics. It makes the mathematics much more complicated, but it also gives the strong interaction some of its most distinctive properties. One of those properties becomes apparent when we ask what happens if we try to pull quarks apart. Our ordinary intuition says that increasing distance should weaken an attraction. This works well for gravity. Move two objects farther apart and their gravitational attraction becomes weaker. Something similar happens with the electric force between charged objects. Increase the distance and the interaction decreases. Quarks refuse to follow this familiar pattern. At very short distances, quarks can behave as though the strong interaction between them is comparatively weak. As we try to separate them, the interaction becomes more difficult to ignore. More energy becomes stored in the strong field. The farther we try to pull the quarks apart, the more energy we must provide. It is common to compare this with stretching something elastic because the resistance increases as the separation grows. Even that analogy eventually breaks down because if you stretch an ordinary elastic object far enough, it snaps and leaves two separate pieces. Trying to separate quarks produces a different outcome. If enough energy is supplied, the system can use that energy to create additional particles. Instead of obtaining one isolated quark on one side and another isolated quark on the other, new quarks and antiquarks can appear and form new composite particles. The result is not a free quark, but a collection of newly created particles in which quarks remain confined. This phenomenon is called quark confinement. No isolated quark has ever been observed under ordinary conditions, despite experiments reaching enormous energies. Physicists can produce situations where quarks behave almost freely over very short distances, and they can infer their behaviour from the patterns produced in particle collisions. But the quarks do not simply emerge alone and remain available for inspection. Nature appears determined to package them into combinations that hide their strong charge from the larger world. There is something mildly amusing about spending billions on particle accelerators only for nature to respond with the subatomic equivalent of no. You may not take that one home. The behaviour at extremely short distances has its own name, asymptotic freedom. It means that quarks interact more weakly when they are extremely close together and probed at very high energies. This discovery was essential because experiments had revealed that quarks inside protons sometimes seem to behave almost like independent particles. That initially looked difficult to reconcile with the fact that quarks were never observed in isolation. Asymptotic freedom and confinement explain how both things can be true. Deep inside a proton, over very short distances, quarks can behave in a relatively free manner. Attempt to separate one from the system over a larger distance, and the strong interaction grows more significant until new particles are produced rather than an isolated quark escaping. The strong interaction is therefore not simply a stronger version of electromagnetism. It follows its own rules, and those rules become especially unusual because gluons themselves take part in the interaction. There is another idea we need before the picture begins to come together, and that is colour charge. Quarks carry a type of strong charge that physicists describe using the word colour. This has nothing to do with the colours visible to human eyes. Quarks are not literally painted red, green, or blue. The terminology is a convenient way of labelling different forms of strong charge and describing how they combine. The important idea is that observable particles such as protons and neutrons are arranged so that their overall colour charge is neutral. Quarks can carry colour charge. Gluons can carry combinations related to it, and the constant exchange of gluons changes the colour states of interacting quarks. It is a dynamic system rather than three coloured beads staying permanently assigned to fixed labels. The word colour makes the theory easier to discuss, but anyone hoping that particle physics finally found a practical use for choosing matching paint samples may be disappointed. This colour structure also helps explain why the strong interaction does not simply leak out of protons over enormous distances. Composite particles such as protons and neutrons are colour neutral overall. The fundamental strong field is mostly confined within them, yet a residual effect remains between neighbouring protons and neutrons. That residual interaction is what helps bind atomic nuclei. The relationship is somewhat similar to the way electrically neutral atoms can still attract one another under certain circumstances, because the internal charges are not meaningless simply because the total charge is zero. The details of the nuclear interaction are different, but the broad lesson is useful. A particle can be neutral overall while still possessing internal structure capable of producing weaker effects outside it. In the case of nuclear matter, that leftover strong interaction operates only over a very short distance, which is exactly what is needed to bind neighbouring protons and neutrons without turning every piece of matter into one enormous nuclear lump. This short range creates a delicate competition inside larger nuclei. Nearby protons and neutrons can attract one another through the residual strong interaction, but every proton also electrically repels every other proton. As nuclei become heavier and contain more protons, that electrical repulsion becomes increasingly difficult to manage. Extra neutrons help because they contribute to nuclear attraction without adding positive electric charge. This is why heavier stable nuclei generally need more neutrons than protons. Eventually, however, nuclei become so large that no arrangement can remain completely stable. The strong interaction is enormously powerful, but it does not have unlimited range, and so it cannot simply overpower all other effects regardless of how many particles are added. This is one of the recurring lessons of physics. Calling something the strongest does not mean it wins every possible competition. The conditions matter. A world champion weightlifter may be stronger than a house cat, but if the contest is climbing a curtain at 3 in the morning, the result could be embarrassing. Nuclear stability has consequences far beyond the nucleus itself. It determines which elements can survive and which radioactive processes occur. It influences how stars generate energy and which nuclei can be built inside them. The strong interaction helps establish the different binding energies of nuclei, and those differences allow nuclear reactions to release energy. In light elements, combining nuclei can sometimes produce a more tightly bound arrangement. This is nuclear fusion, the process that powers stars like the Sun. Deep inside the Sun, hydrogen nuclei are moving in an environment of extreme temperature and pressure. They electrically repel one another, but quantum mechanics gives them a chance to approach closely enough for nuclear processes to occur. Through a sequence of reactions involving more than one fundamental interaction, hydrogen is gradually converted into helium and energy is released. Some of that energy eventually escapes the Sun as radiation and reaches Earth. The warmth you feel in sunlight therefore has a long chain of causes behind it, and strong interaction physics is part of that chain. Larger stars can take nuclear processing further. As conditions change in their interiors, they can create progressively heavier elements through additional nuclear reactions. Carbon, oxygen, and many other nuclei owe their cosmic abundance to stellar processes. When massive stars reach the ends of their lives, violent events can create conditions in which still heavier nuclei form. Those elements can be thrown into space and later incorporated into new stars, planets, and living systems. The iron in blood and the calcium in bones did not begin their history on Earth. Their nuclei were shaped by processes that depend on the rules of nuclear physics, which in turn depend on the strong interaction. The force we cannot directly feel is connected to the material that makes feeling possible. There is no need to dress that up further. The connection is already remarkable enough. The strong interaction also contributes most of the mass of ordinary protons and neutrons, in a way that surprises many people. It is tempting to imagine that the mass of a proton is simply the sum of the masses of its quarks, rather like weighing 3 ingredients and adding the numbers together. The actual picture is very different. The quarks account for only a relatively small portion of the proton mass through their individual masses. Much of the proton mass comes from the energy associated with the strong interaction, including the motion of quarks and the gluon fields inside the proton. This means that much of the mass in ordinary objects is related not merely to the presence of quarks, but to the energetic strong interaction system binding them. When you weigh an ordinary object, a large fraction of what appears on the scale ultimately reflects strong interaction energy inside protons and neutrons. The object may be sitting quietly on the bathroom scale, but the physics responsible for much of that mass is anything but quiet. This is one reason the strong interaction deserves far more attention than it usually receives outside physics. Gravity gets the impressive photographs. Black holes bend light, galaxies collide, planets orbit, and falling objects are available for demonstrations in nearly every room. Electromagnetism has lightning, magnets, lasers, electronics, and the entire visible spectrum. The strong interaction is harder to advertise. Its main work happens inside matter, beyond direct human perception. There is no strong force switch on the wall, and no simple household experiment where you watch a quark politely exchange a gluon. To study it directly, physicists need particle accelerators, high-energy collisions, complex detectors, and careful interpretation of the debris. Yet the interaction itself is present continuously inside every proton and neutron around us. It has been there throughout the entire time you've been listening, operating inside the atoms of your body without requesting attention, or even a modest amount of applause. Particle accelerators allow scientists to investigate this hidden world by colliding particles at very high energies. When protons collide, the internal quarks and gluons can participate in violent interactions. The collision does not simply crack the proton open and scatter a few quarks across the detector. Because of confinement, the outgoing quarks and gluons rapidly produce groups of new particles. These groups often appear as narrow sprays called jets. By examining their energies, directions, and particle content, physicists can reconstruct information about the quarks and gluons involved in the original collision. It is a little like trying to understand what happened inside a locked kitchen by studying every crumb that flies out when the door suddenly opens. Although professional particle physicists may prefer that we do not describe their detectors as extremely expensive crumb collectors, experiments have also created an unusual state of matter called quark-gluon plasma. Under sufficiently high temperatures and densities, quarks and gluons can behave in a state where they are no longer confined into individual protons and neutrons in the usual way. Conditions like this are thought to have existed in the extremely early universe, shortly after its beginning, before matter cooled enough for protons and neutrons to form. Modern particle colliders can reproduce tiny amounts of this state for extremely brief periods by smashing heavy atomic nuclei together at enormous energies. Studying the resulting matter gives physicists information about the strong interaction under conditions very different from those inside ordinary nuclei. It also allows us to investigate a period of cosmic history that cannot be visited directly. The oldest events in the universe leave clues in the behavior of the smallest particles, which is one of those connections physics keeps making whether or not anyone asked it to be so ambitious. At the other extreme, the strong interaction becomes important in some of the densest objects in the modern universe. Neutron stars contain matter compressed to extraordinary densities. Their internal physics depends strongly on how nuclear matter behaves when particles are forced much closer together than they are in ordinary atoms. Scientists are still working to understand the exact composition of the deepest regions of these stars. Some possibilities involve unusual arrangements of nuclear particles, while others may include forms of matter, in which quarks behave differently from those inside ordinary protons and neutrons. Observations of neutron star masses, sizes, collisions, and gravitational waves can therefore tell us something about the strong interaction in extreme conditions. A force that normally hides inside particles smaller than an atom can help determine whether a stellar remnant remains a neutron star or collapses further. Small-scale physics and large-scale astronomy meet in the same problem. All of this begins to explain why calling the strong interaction the strongest force in the universe is both correct and slightly incomplete. Its strength is extraordinary, but the more interesting story is what that strength does. It confines quarks. It creates the internal structure of protons and neutrons. Its residual effects allow atomic nuclei to exist. It influences which elements are stable. It plays a central role in nuclear energy, stellar evolution, the origin of many chemical elements, the properties of neutron stars, and the behavior of matter under some of the most extreme conditions scientists can create or observe. At the same time, it remains almost completely hidden from ordinary experience because it performs nearly all this work across distances so small that our senses have no direct access to them. The next time you pick up an ordinary object, it is worth remembering that what feels simple at our scale is being supported by several layers of physical structure. Your hand interacts with the object mainly through electromagnetism. Gravity gives both your hand and the object weight. Inside the atoms, electrons follow quantum rules. Inside the nuclei, protons and neutrons are bound in arrangements shaped by nuclear forces. Inside each proton and neutron, quarks and gluons participate in the much deeper, strong interaction. Nothing about the object announces these layers. A wooden table remains stubbornly table-shaped. A cup does not become more interesting to look at merely because most of its visible mass depends on quark and gluon dynamics. Physics simply tells us that familiar appearances can rest on mechanisms that are anything but familiar. That brings us to the place where the strong interaction first becomes unavoidable in ordinary matter, the atomic nucleus. We have already seen the puzzle waiting there. Protons carry the same positive electric charge, which means they repel one another, and yet many of them can remain packed inside a region of astonishingly small size. Neutrons join them, nuclear binding holds certain combinations together, other combinations become unstable, and the balance changes as nuclei grow heavier. Understanding why that happens requires a closer look at the nucleus itself, not as a simple collection of little balls, but as a dense quantum system whose stability depends on distance, particle number, nuclear binding, and the short reach of the residual strong interaction. That is where the strongest force begins to leave fingerprints that we can study much more directly, and it is where we can start seeing how something hidden inside quarks becomes responsible for holding entire atomic nuclei together. Once we move inward from the familiar surface of matter and arrive at the atomic nucleus, the strong interaction becomes much easier to appreciate, although the nucleus itself is anything but easy to picture. An atom is already extremely small, but the nucleus occupies only a tiny fraction of the space we normally associate with an atom. If an atom were enlarged until it filled a large building, the nucleus would still be a remarkably small object near the centre. Most of the apparent volume of the atom belongs to the region associated with its electrons, while almost all of the atom's mass is concentrated in the nucleus. That makes the nucleus a wonderfully strange arrangement. It is very small, very dense, and filled with particles that should, at least according to one familiar force, have considerable difficulty remaining together. Protons carry positive electric charge, and positive electric charges repel one another. Put two protons near each other, and electromagnetism tries to push them apart. Put several protons into the tiny space of a nucleus, and the problem becomes even more obvious. Every proton is surrounded by other positive charges, all contributing to the electrical repulsion. If electromagnetism were the only important interaction at that scale, most atomic nuclei would not last. The protons would simply have too much reason to separate. Yet carbon nuclei survive, oxygen nuclei survive, iron nuclei survive, and many other nuclear arrangements remain stable for enormously long periods. Something inside the nucleus is providing enough attraction to overcome that electrical repulsion when the particles are very close together. and that is where the strong interaction begins to reveal itself in a form we can study through nuclear physics. The simplest nucleus belongs to the most common form of hydrogen, which contains only one proton. With only one proton, there is no second positive charge to repel it, so there is no need to explain how several nucleons remain bound together. Things become more interesting as soon as we consider nuclei containing more particles. Helium, for example, can contain 2 protons and 2 neutrons in a very stable arrangement. The 2 protons repel electrically, but the protons and neutrons participate in the attractive nuclear interaction. Neutrons are particularly useful in this balance because they have no net electric charge. Adding a neutron can increase the amount of nuclear attraction without adding another positive electric charge to the nucleus. It would be tempting to imagine neutrons sitting between protons like little cushions that prevent an argument, but the real nucleus is not arranged so neatly. Protons and neutrons are quantum particles. They do not sit in fixed places like marbles glued into a model. Their positions and motions are described through quantum states, and the nucleus behaves as a connected system rather than a tiny mechanical construction. Still, the basic competition remains. The strong nuclear attraction helps bind neighbouring protons and neutrons, while electromagnetic repulsion acts between the positively charged protons. Whether a nucleus survives depends partly on how those effects balance. The word neighbouring matters because the nuclear attraction has a very short range. This makes it quite different from electromagnetic repulsion. A proton inside a nucleus can be strongly influenced by nearby nucleons, but the attractive nuclear effect does not continue across larger distances with anything like the reach of electromagnetism. This short range has major consequences as nuclei become larger. Imagine a small group of people standing close enough to hold hands. Each person can only hold the hands of those immediately beside them. Adding more people makes the group larger, but it does not allow each person to hold hands with everyone else. The attractive nuclear interaction behaves somewhat like that in the sense that nearby nucleons benefit most strongly from it. Electrical repulsion between protons, however, is not limited in the same way. As more protons are added, the amount of repulsion grows across the nucleus. This is why the strong interaction can be the strongest fundamental interaction, and yet still fail to keep every imaginable nucleus stable. Its strength is enormous, but its reach is limited. Nature has not given the nucleus an unlimited supply of nuclear glue. It has given it something much more interesting, a very powerful short-range interaction whose effectiveness depends on how close the particles are and how the entire quantum system is arranged. This balance helps explain a pattern found among stable nuclei. In lighter elements, stable nuclei often contain roughly similar numbers of protons and neutrons. As nuclei become heavier, stable arrangements generally require more neutrons than protons. Those extra neutrons contribute to nuclear binding without increasing the electrical repulsion between positive charges. A heavy nucleus containing only protons would be an exceptionally uncomfortable place. Each proton would be contributing another positive charge, while the short-range attraction would not gain enough reach to compensate indefinitely. Neutrons help, but even they cannot solve the problem forever. Eventually, nuclei become so large that complete stability becomes difficult or impossible. This is why the heaviest elements are radioactive. Their nuclei can exist, sometimes for long periods and sometimes only briefly, but they are not permanently stable arrangements. The internal balance is too demanding. They may transform into lighter nuclei or change their composition through radioactive processes. The nucleus is therefore not simply held together because the strong force wins. It is held together when the particular arrangement of particles creates a sufficiently favourable balance among several effects. The distinction between the fundamental strong interaction and the force between protons and neutrons is important here. When people first learn that the strong force holds atomic nuclei together, it is easy to imagine a single force reaching from one proton to another in exactly the same way that gravity reaches from one planet to another. The deeper picture is different. the fundamental strong interaction acts on quarks, the smaller particles found inside protons and neutrons. Quarks carry a type of charge associated with the strong interaction, and they interact through gluons. Protons and neutrons are combinations of quarks whose overall strong colour charge is neutral. Because of that neutrality, the full fundamental interaction does not simply extend outward from a proton across ordinary distances. What remains between neighbouring protons and neutrons is a residual effect of the strong interaction taking place inside them. In other words, the force binding the nucleus is connected to the strong interaction in much the same way that a faint effect outside a complicated system can reveal much stronger activity taking place within it. The nuclear force is the outside trace of something even more powerful happening inside every proton and neutron. Before quarks were known, physicists had already realized that some short-range attractive force must exist inside the nucleus. The existence of stable nuclei demanded it. They could observe that protons repelled one another electrically, and they knew gravity was far too weak to provide meaningful nuclear binding. The missing interaction had to be strong, but it also had to act only over very small distances, because nuclei had definite sizes, and ordinary atoms were not all sticking together through nuclear attraction. This led physicists to search for ways of describing the force between nucleons. One historically important idea involved the exchange of particles called mesons. A Japanese physicist named Hideki Yukawa proposed that a short-range nuclear force could arise through the exchange of a massive particle. The basic reasoning was that the limited range of the interaction should be related to the mass of the particle associated with transmitting it. Particles resembling the expected mesons were later discovered, and the theory became an important step toward understanding nuclear forces. Today, we know that mesons are themselves made from quarks and antiquarks, so the explanation eventually leads back to the deeper theory of the strong interaction. This layered understanding is common in physics. At one level, it can be useful to describe protons and neutrons interacting through an effective nuclear force. Go deeper and those protons and neutrons become complicated quark systems, and the residual nuclear force becomes a consequence of quantum chromodynamics. Neither description is useless simply because another level exists underneath it. If you want to understand the orbit of the Moon, you do not normally need to calculate the quantum behaviour of every particle inside Earth. If you want to understand chemistry, you usually do not begin by tracking every gluon inside every proton. Physics works by choosing the level of description appropriate to the problem. For many questions about nuclei, protons and neutrons are useful starting points. For questions about why protons and neutrons have the properties they do, we need quarks and gluons. The universe seems perfectly comfortable with giving us several layers of explanation, perhaps because it knows that one layer would make textbooks suspiciously thin. The nucleus itself also has structure beyond simply counting how many protons and neutrons are present. Quantum mechanics restricts the ways nucleons can arrange themselves. Protons and neutrons belong to a family of particles called fermions, and identical fermions cannot all occupy exactly the same quantum state. This principle strongly influences the structure of atoms through the behaviour of electrons, and it also matters inside nuclei. Protons occupy nuclear quantum states, and neutrons occupy their own states. These states can be organised into groups that physicists describe using a nuclear shell model. The idea has some similarity to the electron shells of atoms, although the details are different. Certain numbers of protons or neutrons fill nuclear shells in especially stable ways. These particular particle counts are known as magic numbers. It is an unusually cheerful term for a subject involving dense quantum systems, but it reflects a genuine pattern. Nuclei with completed shells can have additional stability, and this helps explain why some combinations of protons and neutrons behave differently from nearby combinations. Another useful description treats the nucleus more collectively, almost like a tiny drop of quantum liquid. In this picture, the protons and neutrons are not considered only as individual particles occupying separate states. The nucleus can also respond as a whole. It can vibrate, rotate, stretch into slightly different shapes, and under certain conditions split into smaller nuclei. This liquid drop picture becomes useful when studying processes such as nuclear fission. A heavy nucleus can become deformed, with different parts pulling away from each other while the short-range nuclear attraction tries to keep the whole system together. Electrical repulsion between the many protons favours separation. If the deformation becomes large enough, the balance can tip and the nucleus can divide. The two new nuclei then move apart because their positive charges strongly repel one another. Energy is released in the process because the final nuclear arrangement can be more tightly bound than the original heavy nucleus. Once again, the strongest interaction in nature does not simply prevent anything from ever breaking. It creates a landscape of possible nuclear arrangements, some more stable than others. Binding energy provides one of the clearest ways to describe this nuclear stability. When protons and neutrons form a bound nucleus, the complete nucleus has less energy than those same particles would have if they were all separated. Energy must therefore be supplied to pull the bound system apart. The more strongly bound a nucleus is, the more difficult the separation becomes. This has a surprising consequence for mass because energy contributes to the total mass of a physical system. A bound nucleus can weigh slightly less than the total weight of its separated protons and neutrons. The missing amount has not vanished. It corresponds to the energy released when the bound system formed. In nuclear reactions, changes in binding can therefore release enormous amounts of energy. This is not because nuclei contain tiny hidden explosions waiting impatiently for someone to notice them. It is because rearranging nuclear particles can move the system from one energy configuration to another. The pattern of nuclear binding explains why both fusion and fission can release energy. Light nuclei can often release energy by joining into heavier, more tightly bound nuclei. Very heavy nuclei can release energy by splitting into intermediate-sized nuclei that are also more tightly bound. Between these extremes lies a region containing some of the most tightly bound nuclei in nature. This is one reason stellar fusion does not continue releasing energy forever, by simply combining everything into heavier and heavier elements. In stars, fusion of light nuclei can provide energy through several stages, but eventually the energetic advantage changes. The details depend on the particular nuclei involved, and stellar evolution becomes more complicated as heavier elements are produced. Still, the overall behaviour traces back to nuclear binding, which traces back to the strong interaction and its competition with electric repulsion. The Sun gives us a familiar example. Deep in its core, hydrogen nuclei exist in extremely hot, dense conditions. Most of the time, two positively charged nuclei approaching one another are pushed apart by electromagnetic repulsion before they can get close enough for the nuclear attraction to dominate. This creates a barrier to fusion. Classical intuition would suggest that a particle without enough energy to overcome a barrier simply cannot pass through it. Quantum mechanics allows another possibility. There is a chance that the nuclei can reach the other side of the barrier through quantum tunneling. Once they approach closely enough, the nuclear interaction becomes important and reactions can occur. The Sun therefore depends on an unusual partnership. Electromagnetism resists the approach. Quantum mechanics allows occasional close encounters. The weak interaction participates in key transformations, and the strong interaction helps determine the nuclear binding of the resulting particles. The steady sunlight arriving through a window has a rather crowded list of contributors. Inside more massive stars, nuclear reactions can build heavier elements. Helium can eventually participate in reactions that create carbon. Carbon can be involved in further reactions under hotter conditions. Massive stars may continue through several stages, building nuclei such as oxygen, neon, magnesium, silicon, and eventually elements near iron. Each new stage requires more extreme conditions, and the star changes as different nuclear fuels become available. None of this would be possible without nuclei having the particular binding properties created by the strong interaction. Stellar evolution is therefore partly a story about gravity forcing matter together, and nuclear physics deciding what reactions become possible once it gets there. Gravity provides the pressure, but nuclear interactions determine much of what happens in response. When a massive star can no longer gain enough support from its current nuclear reactions, gravity may cause its core to collapse. Under these extreme conditions, nuclear matter is pushed into a regime that ordinary atoms never experience on Earth. Electrons and protons can be transformed through processes that produce large numbers of neutrons and neutrinos. The collapse may help trigger a supernova, and the resulting event can scatter newly produced elements into space. Some of the heaviest nuclei are associated with environments where neutrons are available in enormous numbers, and nuclei can capture them rapidly. Later, radioactive transformations can change the composition into heavier elements. Gold, platinum, and other heavy elements have histories connected to violent astrophysical events, including neutron star collisions and certain stellar explosions. The stable objects in a jewellery box can therefore contain nuclei whose ancestors were assembled under conditions that would make an ordinary laboratory seem extremely underprepared. Nuclear density becomes especially impressive when we consider neutron stars. Ordinary atoms contain large regions associated with electrons around very tiny nuclei, which means everyday matter has enormous amounts of space compared with nuclear dimensions. In a neutron star, gravity compresses matter so strongly that the usual atomic structure cannot survive. Matter reaches densities comparable to those inside atomic nuclei. A neutron star may contain more mass than the Sun while being only about the size of a city. Its internal structure is still an active area of research because the exact behaviour of matter at such extreme densities depends on nuclear interactions that are difficult to reproduce completely in laboratories. Near the outer regions, the matter can contain nuclei and free neutrons. Deeper inside, the composition may change substantially. Scientists investigate possibilities involving unusual nuclear states and potentially forms of matter where quarks behave differently from those inside isolated protons and neutrons. This gives nuclear physics an unusual connection between the smallest and largest scales. Experiments involving atomic nuclei on Earth can help physicists understand neutron stars thousands of light years away. Observations of neutron stars can, in turn, provide clues about how nuclear matter behaves at densities beyond those easily reached in terrestrial experiments. When two neutron stars collide, gravitational waves carry information about how the stars deform before merging. That deformation depends partly on how compressible their matter is, which depends on the interactions among particles inside them. So a gravitational wave detector measuring distortions in space can indirectly teach us something about the strong interaction. Physics enjoys these improbable partnerships. A detector kilometers across can help answer questions about forces acting across distances far smaller than an atom. Even without neutron stars or supernovae, the nucleus contains enough puzzles to keep physicists busy. Different nuclei can have different shapes. Some are approximately spherical, while others are elongated or flattened. Some can briefly occupy excited states, and then release energy as they move into lower energy configurations. Some contain unusual arrangements where groups of nucleons behave as smaller clusters within the larger nucleus. Some exist only for tiny fractions of a second before decaying. Modern laboratories can create exotic nuclei with unusually large proportions of neutrons or protons, and study how their structures change as the usual balance is pushed toward its limits. These experiments help reveal where nuclear stability ends and how the strong interaction behaves in systems unlike the stable elements around us. One particularly interesting region occurs near what physicists call the drip lines. Add too many neutrons to a nucleus, and eventually an additional neutron cannot remain bound. Add too many protons and the same problem can occur on the proton-rich side. The nucleus has reached the edge of its ability to hold another particle. These limits are useful because they test our understanding of nuclear forces under unusual conditions. A theory that works beautifully for common stable nuclei may face new difficulties when asked to describe an exotic nucleus containing a very uneven balance of protons and neutrons. Nature has a way of revealing weaknesses in our models by choosing the least convenient possible test case. There is also an important saturation property of the nuclear force. Because the effective attraction between nucleons is short-ranged, a nucleon mainly interacts strongly with a limited number of nearby neighbours rather than equally with every particle in the nucleus. This helps explain why the density of nuclear matter remains roughly similar across many nuclei. Adding more nucleons usually makes a larger nucleus, instead of crushing all the existing nucleons into an endlessly denser object. This is very different from what might happen if every nucleon strongly attracted every other nucleon regardless of distance. Nuclear matter has a characteristic density because the interaction and quantum restrictions produce a preferred spacing. The nucleus is crowded, but it is not simply a point where particles are piled without limit. At extremely short separations, the effective interaction between nucleons can also become strongly repulsive. This prevents protons and neutrons from being compressed arbitrarily close together under ordinary nuclear conditions. The complete nuclear interaction is therefore more complicated than saying that protons and neutrons attract each other. At useful nuclear distances, attraction helps bind them. Push them too close, and other effects become important, producing resistance to further compression. This behaviour matters enormously in dense matter. It influences the structure of nuclei and contributes to the physics, determining how neutron stars resist gravitational collapse. The strongest interaction is not merely a rope pulling particles together, it creates a detailed relationship between distance and energy, and that relationship determines what arrangements of nuclear matter are possible. The existence of the nucleus also reminds us that stable matter is not the same thing as motionless matter. A nucleus can remain unchanged for billions of years, while its quantum constituents remain anything but static. Protons and neutrons occupy states with characteristic energies and momenta. Inside each proton and neutron, quarks and gluons form an even more active system. Stability means that the overall quantum state does not have an available pathway that forces it to transform quickly. It does not mean that every component has stopped moving. This distinction is easy to overlook because stable objects in ordinary life often seem associated with stillness. A stone resting on a table appears stable because nothing visible is changing. At the microscopic level, however, both the stone and table contain atoms filled with quantum activity. The calm surface of matter is an emergent appearance. That quiet stability is particularly impressive when we consider how much of ordinary matter depends on nuclear arrangements surviving over cosmic times. Carbon nuclei formed in ancient stars can remain intact through the death of the star, travel through interstellar space, become part of a new planetary system, enter the chemistry of a living organism, and eventually become part of a person listening to a science video very late at night. The nucleus does not know any of this has happened, of course. It has no opinion about stars, biology, or bedtime. It simply continues obeying the same physical rules. Yet the fact that those rules permit long-lived nuclei is one of the reasons complex structures can accumulate in the universe, instead of constantly dissolving back into simpler particles. As useful as the picture of protons and neutrons is, however, it leaves one question unresolved. We have said that the force between nucleons is a residual effect of the strong interaction, but that immediately raises the question of what the full interaction looks like inside the nucleons themselves. A proton seems small and simple when it is drawn as a single circle in an atomic diagram, but once we examine it closely, that circle disappears into a much busier world. Quarks carry the strong charge, gluons transmit and participate in the interaction, temporary quark and antiquark contributions appear within the quantum system, and much of the proton's mass comes from the energy associated with this activity, rather than merely from adding up the masses of its quarks. The force that holds the nucleus together is therefore only the outermost sign of something much deeper. To understand where its extraordinary strength really comes from, we have to move inside the proton and neutron themselves, where the convenient picture of nuclear particles gives way to quarks, gluons, and a kind of charge that physics decided with suspicious confidence to name after colours. Once we look inside a proton or neutron, the tidy picture of the atomic nucleus becomes much less tidy. A proton may appear in a school diagram as a small circle with a positive sign inside it, and a neutron may appear beside it as another circle without a charge. But neither particle is really a featureless little ball. Each contains quarks, and those quarks are held together by gluons through the strong interaction. The word gluon comes from the idea of glue, which makes the basic job sound pleasantly straightforward. Quarks are inside, gluons hold them together, and everyone can go home early. Unfortunately for anyone hoping for a simple explanation, the reality is much busier. Gluons are not little droplets of adhesive sitting between quarks. They are quantum particles associated with the strong field, and they participate in the very interaction they transmit. The quarks are not stationary objects waiting to be glued into position either. They move, exchange energy and momentum, interact through gluons, and exist as part of a constantly active quantum system. A proton that looks perfectly calm from the outside contains an interior that is anything but calm. The quarks most important for ordinary protons and neutrons are called up quarks and down quarks. A proton contains 2 up quarks and 1 down quark in the simplest description, while a neutron contains 1 up quark and 2 down quarks. That small difference is enough to change the electric charge of the particle. The up quark carries a positive fractional electric charge, while the down quark carries a negative fractional charge. Combined in the appropriate way, the 3 quarks in a proton produce 1 positive unit of electric charge, while the 3 in a neutron add to 0. Fractional charges may sound slightly suspicious the first time you encounter them, because everyday matter always seems to present electric charge in neat whole amounts. Quarks are one reason nature can get away with that. They are normally confined inside particles whose total electric charges combine into the familiar values we observe. You do not usually meet 1/3 of an electron charge wandering around the kitchen looking for somewhere to sit. The quarks remain hidden inside larger particles, and their fractional charges become part of the internal bookkeeping. There are other types of quarks as well. Physicists currently know 6 varieties, usually called flavors. Along with up and down quarks, there are strange, charm, top, and bottom quarks. The names are not descriptions of personality. A strange quark is not more mysterious than a charm quark, and a top quark has no particular interest in being physically above the others. Particle physics accumulated its vocabulary over decades of discoveries, and the result sometimes sounds like a list produced during a very relaxed meeting. Most ordinary matter around us is built from up and down quarks, because the heavier quarks are unstable and tend to transform into lighter particles. Those heavier quarks can still be produced in high-energy collisions and are essential for understanding the full structure of particle physics. But the protons and neutrons making up everyday atomic nuclei rely primarily on the 2 lightest quark flavors. If quarks carried only electric charge, electromagnetism would already give them ways to interact, but the defining property involved in the strong interaction is something different. Physicists call it color charge. The word color is purely a label. It has nothing to do with visible red, green, or blue light, and a quark would not look colored even if we somehow had a microscope capable of producing an ordinary photograph of one. The term became useful because there are 3 varieties of strong charge associated with quarks, and physicists borrowed the names red, green, and blue as a convenient way to distinguish them. The analogy works particularly well because suitable combinations can produce a color-neutral state, rather like combining the 3 familiar colors of light to obtain white. Again, nothing is literally glowing red or green inside the proton. The language is doing organizational work, not describing appearance. A proton contains 3 main quarks arranged so that its overall color charge is neutral. The same is true of a neutron. This neutrality is extremely important because isolated particles found in ordinary matter do not expose a net color charge to the outside world. Quarks carry color, but the composite particles we normally observe are color-neutral combinations. There is another common kind of composite particle called a meson, which consists of a quark and an antiquark. The quark and antiquark carry complementary strong charges that also combine into a neutral whole. These rules are part of the reason quarks are found in particular groups rather than simply appearing alone. The strong interaction does not allow nature to scatter individual colour-charged particles around freely under ordinary conditions. Gluons make this picture considerably more interesting because gluons themselves carry strong colour information. This is one of the major differences between the strong interaction and electromagnetism. The particle associated with the electromagnetic interaction is the photon. Photons can carry energy and momentum, but they do not carry electric charge. Because they lack electric charge, photons do not directly interact with one another through ordinary electromagnetism in the same way that charged particles do. Gluons are different. They participate in the strong interaction because they carry the type of charge involved in it. A gluon can therefore interact with another gluon. The messenger is also part of the conversation. Imagine a postal service in which every letter can write back to other letters while being delivered, and you begin to see why the accounting becomes difficult. When a quark emits or absorbs a gluon, its colour state can change. The gluon carries the necessary strong charge information so that the overall system continues obeying the conservation rules of the interaction. This means the colour arrangement inside a proton is not static. We should not imagine one quark permanently labelled red, another permanently green, and another permanently blue, politely holding those assignments for the lifetime of the proton. Gluon exchanges continually alter the colour states. The proton remains colour neutral overall, but the internal details are constantly changing. That gives the interior of a proton a much more active character than any simple drawing can show. The modern theory describing all this is called quantum chromodynamics. The name may sound intimidating, but each part tells us something useful. Quantum tells us that the theory belongs to quantum physics. Chromo refers to colour charge. Dynamics refers to the interactions and changes taking place. Quantum chromodynamics is therefore the quantum theory of how colour-charged particles behave. It is one of the central parts of the standard model of particle physics, and has been tested through a large range of experiments. The theory successfully describes many observations involving protons, neutrons, particle collisions, jets, and the behaviour of strongly interacting matter. It is also famously difficult to calculate in many situations because the gluons interact with each other, turning what might have been a complicated problem into a much more complicated problem, presumably because physicists were not already busy enough. One of the most surprising features of quantum chromodynamics is that the strength of the interaction depends on the distance and energy scale being examined. At very short distances, quarks behave more freely. The effective strong interaction becomes weaker. This behaviour is called asymptotic freedom. The discovery of asymptotic freedom helped solve a major puzzle that appeared in experiments probing protons at very high energies. When energetic particles were fired into protons, the scattering patterns suggested that the objects inside the proton behaved almost as though they were independent point-like particles. That seemed strange because if the strong interaction was supposed to be extremely powerful, why did the quarks appear almost free when examined closely? The answer turned out to be that the strong interaction becomes weaker at those extremely short distances. When quarks are packed very close together, they can move in a way that looks comparatively independent. The deeper we probe at high energies, the more this near freedom becomes apparent. That does not mean the strong interaction disappears, it means its effective strength changes with scale. This is not how ordinary intuition expects a force to behave. We're used to thinking that close objects should interact more strongly, and distant objects more weakly. The strong interaction has a different pattern because of the behaviour of the gluon field. Move quarks farther apart, and the situation changes dramatically. Instead of fading away, the interaction becomes more difficult to overcome. Energy builds in the strong field connecting the separated colour charges. The farther one tries to pull the quarks apart, the more energy must be supplied. A common comparison is a stretched elastic band. Pull gently, and resistance appears. Pull farther and the stored energy increases. The comparison works for a while, but then nature takes an unusual turn. An ordinary elastic band eventually breaks and leaves two separate pieces. If enough energy is put into separating quarks, the strong field does not simply snap and leave a free quark at each end. The supplied energy can produce new quarks and antiquarks. These new particles combine with the original quarks, creating new color-neutral particles. The result is that the quarks remain confined even after an enormous amount of energy has been used trying to separate them. This is quark confinement, one of the defining properties of the strong interaction. Physicists have never observed an isolated quark under ordinary conditions. They can produce quarks in collisions and study the patterns generated by them, but the quarks do not travel freely into the detector as single particles. Instead, they become part of new hadrons, the general name for particles made from quarks. Protons and neutrons are hadrons, mesons are hadrons. Many short-lived particles created in accelerators belong to the same broad family. When a high-energy quark is produced, it eventually leads to a spray of hadrons moving in roughly the same direction. This spray is called a jet. Experiments can study jets to learn about the quark or gluon that initiated them, even though the original color-charged particle never reaches the detector by itself. It is almost like trying to study a person who refuses to appear in photographs but leaves a very distinctive trail of receipts wherever they go. You never see the person directly, but enough evidence remains that you can reconstruct a surprising amount about what happened. Particle physicists use the energies, directions, and types of particles inside jets to test the predictions of quantum chromodynamics. Large detectors at particle accelerators are designed to record huge numbers of collision events because the patterns become meaningful through careful statistical analysis. A single collision can look chaotic. Millions or billions of collisions reveal structure. The inside of a proton is similarly more complicated than the familiar picture of three quarks might suggest. The two up quarks and one down quark are called the valence quarks, because they determine the basic identity and quantum numbers of the proton. But the proton also contains gluons and temporary quark and antiquark activity generated by the strong field. These additional contributions are often described as a sea of quarks and antiquarks. The phrase is useful as long as we remember that this is not an actual fluid sloshing around inside the proton. It refers to the quantum activity produced by the interactions among the fields. Gluons can contribute to processes that create quark and antiquark pairs, and those particles can disappear again through further interactions. The proton is therefore not three quarks sitting in empty space. It is a strongly interacting quantum system filled with ongoing field activity. This helps explain one of the most surprising facts about ordinary matter. The masses of the individual quarks inside a proton account for only a relatively small part of the proton's total mass. Most of the proton's mass comes from the energy associated with the strong interaction, including the energy of the gluon fields and the motion of the quarks. The same general statement applies to neutrons. This means that much of the mass of ordinary matter is not simply the combined resting mass of the basic quarks. It arises from the energy of the strong interaction inside protons and neutrons. The mass of a chair, a stone, a human body, or a cup of tea is therefore deeply connected to the behavior of quarks and gluons inside atomic nuclei. That can feel peculiar because mass seems like one of the most solid and uncomplicated properties an object can have. Put something on a scale and a number appears. Nothing about that measurement suggests a storm of quantum fields inside protons, yet the scale is indirectly responding to a property whose origin lies largely in strong interaction energy. The quarks themselves are important, of course, but much of what gives ordinary nuclear matter its mass comes from the energetic system binding those quarks together. The strong force is not merely holding pre-existing heavy pieces in place. Its own dynamics are responsible for much of the mass we associate with those particles in the first place. Gluons are central to that dynamics. There are several possible gluon states, each carrying combinations of colour and anti-colour information. The exact language can become technical very quickly, but the important idea is that gluons can exchange colour between quarks while keeping the entire system consistent with the rules of the strong interaction. Because gluons themselves carry colour charge, they can emit and absorb other gluons. This creates a network of interactions that does not have a simple equivalent in classical physics. A proton is therefore held together not by a few straight lines of force running neatly between three fixed points, but by a constantly evolving quantum field. Under normal conditions, confinement keeps quarks inside hadrons, but there are extreme conditions where strongly interacting matter behaves differently. In the early universe, temperatures were so high that protons and neutrons had not yet formed in their familiar stable way. Instead, quarks and gluons existed in a hot state known as quark-gluon plasma. Modern experiments attempt to recreate tiny amounts of this matter by colliding heavy atomic nuclei at enormous energies. For an extremely brief time, the energy density becomes high enough for quarks and gluons to behave in a state that is not confined into individual protons and neutrons in the ordinary manner. At first, researchers expected quark-gluon plasma might behave somewhat like a gas of nearly independent particles. Experiments instead revealed that it can behave more like an extremely well-flowing liquid, with remarkably strong collective behaviour. The strong interaction had once again managed to make the supposedly simple picture less simple. Studying this state helps physicists understand both quantum chromodynamics and the conditions of the very early universe. It provides a connection between microscopic particle experiments conducted in laboratories and the first moments of cosmic history, when the universe itself was hot enough that the matter around us today had not yet settled into protons, neutrons, nuclei, atoms, planets, or anything that would fit comfortably on a breakfast table. As the early universe expanded and cooled, quarks became confined into hadrons. Protons and neutrons appeared as stable combinations, and later those particles participated in the formation of atomic nuclei. Much later still, electrons became bound to nuclei and neutral atoms could form. Stars, galaxies, planets, chemistry, and eventually life followed after enormous stretches of cosmic evolution. At the bottom of that sequence lies the fact that quarks and gluons behave according to the rules of the strong interaction. If those rules were substantially different, the stable building blocks of matter could be different as well. The strong interaction also determines which composite particles can exist. Quarks are not free to combine in arbitrary ways. Certain combinations produce baryons, which include protons and neutrons. Other combinations produce mesons. Many of these particles are unstable and survive only briefly before transforming into other particles. Particle accelerators have revealed a large collection of such states, turning what once seemed like a small list of elementary particles into what looked for a time like an overcrowded catalogue. The quark model helped bring order to that growing collection by showing that many apparently different particles were really different combinations and arrangements of a smaller number of quark types. This was an important change in how physicists understood matter. A proton and neutron were no longer unrelated fundamental objects that simply happened to live together in nuclei. They became members of a much larger family of particles built according to common underlying rules. Quarks provided the ingredients, while the strong interaction determined how those ingredients could combine. The confusing variety of hadrons began to look less like nature had invented hundreds of unrelated particles and more like a set of variations produced from a smaller toolkit. It was rather like discovering that an enormous restaurant menu is mostly built from a surprisingly modest pantry, although the kitchen in this case operates using quantum fields and would probably fail several local safety inspections. Even now, calculating the properties of hadrons directly from quantum chromodynamics can be difficult because the strong interaction becomes very strong at the distances relevant to confinement. Ordinary approximation methods that work well when an interaction is weak become less reliable. Physicists use powerful computational techniques, including an approach called lattice quantum chromodynamics, in which space and time are represented computationally as a discrete grid for the purpose of performing calculations. Large computers can then simulate aspects of quark and gluon behavior and estimate properties such as hadron masses. These calculations have become increasingly precise and provide an important bridge between the basic theory and the particles observed in experiments. The difficulty is itself revealing. We know the fundamental rules of the strong interaction remarkably well, yet extracting every consequence of those rules can still be enormously challenging. Knowing the ingredients and instructions does not always make the final result obvious. Anyone who has followed a supposedly simple recipe and somehow produced something with the structural integrity of roof insulation may already understand the principle. In strong interaction physics, the complication comes from countless mutually interacting quantum degrees of freedom rather than an unreliable oven, but the feeling is not entirely unrelated. Quarks and gluons therefore give us a much deeper meaning for the phrase strong force. The interaction is not simply a powerful attraction pulling particles together. It is a complete quantum system with charges that change, force carriers that interact with one another, an effective strength that changes with distance, confinement that prevents isolated quarks from appearing, and field energy that supplies much of the mass of ordinary matter. The proton beneath a simple positive sign in a classroom drawing contains all of this. The neutron beside it does too. What looks like the calm foundation of the atomic nucleus is supported by a restless interior. There is still one piece of this story that deserves a much closer look because it controls nearly everything we have just described. Color charge is more than a convenient label attached to quarks. Its unusual rules explain why gluons interact with one another, why observable particles are color neutral, why quarks remain confined, and why the strong interaction behaves so differently from electromagnetism. Understanding that color has nothing to do with actual color is only the beginning. The more interesting question is how three kinds of strong charge can organize the behavior of matter while remaining completely invisible to our ordinary senses, and why the universe seems determined to hide every exposed trace of color inside particles that look neutral from the outside. Color charge is one of those phrases in physics that sounds much more familiar than it really is. The word color immediately suggests something visible, something you might find in a paint box on a television screen, or on the side of a cereal packet designed by someone who had access to far too much red ink. But when physicists talk about color charge, they are not describing anything that has a visible color at all. Quarks are not red, green, or blue in the ordinary sense, and gluons do not glow with tiny shades that could be seen if only we had a powerful enough microscope. The names are labels chosen because they provide a convenient way to keep track of three different forms of the charge involved in the strong interaction. The terminology turned out to be surprisingly useful, but it also created one of the easiest misunderstandings in particle physics. Color charge is real as a physical property, but the color part is only an analogy. To understand why physicists needed this extra kind of charge in the first place, it helps to remember what an electric charge does. Some particles carry positive electric charge, some carry negative electric charge, and some are electrically neutral. Electric charge determines how a particle participates in the electromagnetic interaction. Opposite charges attract, like charges repel, and particles with the electric charge can exchange photons as part of their electromagnetic interactions. Color charge plays a somewhat similar organizing role for the strong interaction, but the rules are more complicated. Instead of only two basic varieties corresponding loosely to positive and negative, quarks can carry one of three types of color charge. These are conventionally called red, green, and blue. Antiquarks carry corresponding anticolors. Again, none of this should be pictured as actual pigment. A red quark is not something that would match a red sock, and if you somehow put one under a lamp, it would not solve the problem by looking maroon. The reason three types are useful becomes clear when we consider the particles quarks form. Protons and neutrons each contain 3 valence quarks, and the combined color charge of those quarks must form an overall neutral state. Physicists call such a state colorless or color neutral. The language of ordinary color provides a convenient analogy because red, green, and blue light can combine to give white light. In the same way, the 3 different color charges in a baryon can combine into a state with no exposed net color charge. The comparison should not be taken too literally, but it gives us a tidy way to remember what is happening. A proton can contain quarks carrying different color charges, while the proton itself is color neutral as a whole. This requirement of color neutrality is one of the most important features of the strong interaction. Isolated color charge does not appear freely in ordinary matter. The particles we observe directly are organized into combinations whose overall color charge is neutral. 3 quarks can combine into a baryon such as a proton or neutron. A quark and an antiquark can combine into a meson, with the color and anticolor arranged so that the complete particle is neutral. Other more complicated combinations can also satisfy the rules, but the same basic principle remains. Nature does not casually leave exposed color charge lying around. The fact that quarks can change color charge makes the picture even stranger. If a proton contains 3 quarks whose total state is color neutral, it does not mean one quark remains permanently red, another remains green, and another remains blue, like 3 employees who were assigned badges on their first day and never changed departments. The quarks continually interact by exchanging gluons. During these interactions, the color state of a quark can change. A quark that was in one color state can emit or absorb a gluon and end up in another. The gluon carries the necessary combination of color information so that the total strong charge remains properly balanced. The individual labels shift, but the overall proton remains color neutral. That means the interior of a proton is not a frozen arrangement of 3 differently colored objects. It is a constantly changing quantum system. Color is being exchanged through the gluon field. Quarks alter their color states. Gluons interact. Additional quark and antiquark activity contributes to the structure. If we could somehow slow down and enlarge the quantum processes inside a proton, we would not see 3 quiet points sitting politely in a triangle. We would find an active network of interactions that never settles into anything resembling the simple diagrams used in introductory explanations. Those diagrams are useful, but they are more like a map of a train network than a live view of every passenger, signal, delay, and person standing in the wrong carriage. Gluons are what make color charge especially different from electric charge. The photon, which carries the electromagnetic interaction, is electrically neutral. It can transmit electromagnetic effects between charged particles without itself possessing ordinary electric charge. Gluons are not neutral in the same way with respect to the strong interaction. They carry combinations of color and anticolor, which means they participate directly in the force they transmit. A gluon can interact with another gluon because both are involved in the strong charge system. This self-interaction is responsible for much of the unusual behavior of the strong force. If gluons behaved more like photons and did not carry strong charge themselves, the theory would look very different. Instead, the strong field can interact with itself. Gluons can influence other gluons, which can influence still more gluons, producing a network of quantum activity around color-charged particles. This changes how the force behaves with distance, and helps explain both asymptotic freedom and confinement. The strongest interaction in nature gains many of its strangest properties from the fact that its messengers are not merely delivering messages, they are involved in the argument. There are 8 types of gluons in the theory, although it is safer not to imagine 8 tiny coloured balls flying back and forth inside every proton. The number comes from the mathematical structure governing how the different colour and anticolor states can combine. Some combinations are physically distinct, while one overall neutral combination is not included as a separate gluon in the same way. The details become deeply mathematical very quickly, so for our purposes the important point is simpler. Gluons come in several allowed strong charge states, and those states let them transfer color charge between quarks, while preserving the total rules of the interaction. Suppose a quark changes from one colour state to another. That change cannot happen without the strong charge being accounted for. The emitted or absorbed gluon carries the appropriate difference. This resembles bookkeeping, although the bookkeeping is happening within a quantum field rather than inside an office where someone has misplaced the receipts. Every interaction must respect conservation laws. Nothing simply loses a strong charge and hopes nobody notices. Colour charge also helps explain why quarks behave differently at different distances. At extremely short distances, quarks can interact relatively weakly. They still participate in the strong interaction, but the effective strength becomes smaller as the distance decreases. This is asymptotic freedom. As the quarks move farther apart, the self-interacting gluon field behaves in such a way that the effective interaction becomes stronger rather than weaker. This is almost the opposite of what everyday intuition would expect from a force. With electricity, we often picture field lines spreading outward through space. As the distance increases, the influence becomes weaker because the field spreads over a larger region. For the strong interaction, the gluon self-interactions prevent the colour field from spreading out in quite the same way. Instead, the field between separated quarks tends to become concentrated into something more like a narrow tube of strong field. As the quarks are separated farther, more energy becomes stored in that field. This is one way to picture why separating quarks becomes increasingly difficult. The comparison to a stretched elastic band is useful again. Imagine two objects connected by something that resists being stretched. Pull them a little, and some energy is stored. Pull them farther, and more energy is stored. The strong field behaves somewhat like that, although there is no actual elastic material between quarks. The crucial difference appears when enough energy has accumulated. Rather than producing two isolated quarks, the system can create a new quark and antiquark pair. The original connection effectively reorganizes into two new color neutral particles. The attempt to free one quark produces more particles instead. Color charge is therefore deeply connected to confinement. If quarks did not carry this particular kind of charge, and if gluons did not interact with one another through it, the strong interaction would not have the same tendency to lock quarks inside hadrons. Ordinary protons and neutrons exist because three quarks can combine into color-neutral states. Mesons exist because quark and antiquark color charges can cancel. The absence of free quarks is not an unrelated curiosity. It follows from the way color charge behaves. This also explains why we do not experience color charge directly in ordinary life. The matter around us is made from atoms. The nuclei contain protons and neutrons, and those particles are already color neutral. The electrons outside nuclei do not carry color charge at all. So at the scale of complete atoms, there is no exposed color charge producing a long-range strong force between objects. Your hand does not strongly bind to a table, because the protons in your hand and the protons in the table are individually hiding their color inside color-neutral combinations. There is a residual strong effect between neighboring protons and neutrons in nuclei, but that is already much weaker and much shorter range than the fundamental interaction between quarks. By the time we reach the scale of separate atoms and everyday objects, the strong interaction has effectively disappeared from direct view. Electromagnetism takes over as the main interaction controlling chemistry, materials, light, and the contact forces we notice. Color charge remains buried several layers down. The word buried is useful because it reminds us how much physical structure sits beneath ordinary matter. An everyday object can be electrically neutral overall, while containing enormous numbers of positive protons and negative electrons. Those charges are hidden through balance. Go one level deeper and each proton is color neutral overall while containing quarks with strong color charge. Matter repeatedly hides active internal properties inside larger neutral structures. From a distance, everything looks quiet. Up close, it becomes a bookkeeping problem that would make an accountant reconsider several career choices. Color charge also separates quarks from particles such as electrons. Electrons carry electric charge, but they do not carry color charge. This means electrons do not participate directly in the strong interaction. A quark can interact electromagnetically because it carries electric charge, and it can interact strongly because it carries color charge. An electron participates in electromagnetism but not the strong interaction. This difference helps define the families of particles in the Standard Model. Quarks belong to the class of particles that experience the strong interaction. Leptons, including electrons and neutrinos, do not carry color charge. This simple distinction has enormous consequences. If electrons carried color charge, atomic structure would be radically different because they would participate in confinement. Instead of forming the familiar diffuse quantum states around nuclei, they might become locked into strongly interacting composite particles. Chemistry as we know it would disappear. Fortunately, the electron appears perfectly content with its existing responsibilities and has not requested additional work. The three color states are also part of the explanation for why certain hadrons can exist without violating other quantum rules. This became historically important when physicists were trying to understand particles containing three apparently identical quarks. Quantum mechanics has strict rules for identical fermions, and some observed particles seem to create a problem if quarks had only the properties then known. Introducing an additional three-valued property, color charge, resolved the issue. The quarks could be identical in several respects while occupying different color states, allowing the complete quantum state to satisfy the required symmetry rules. This is a lovely example of how physicists sometimes discover unseen properties. Nobody observed visible color on a quark and decided to build a theory around it. Instead, the known particles behaved in ways that required an additional internal degree of freedom. The theory needed a hidden label with three possible states. Later, quantum chromodynamics developed that idea into the full theory of the strong interaction. Color charge was not invented simply because 3 was a convenient number. It helped explain real patterns in particle behavior. Experiments then tested the theory through high-energy collisions. When particles collide at enormous energies, the way quarks and gluons scatter depends on color dynamics. The patterns of jets produced in detectors can be compared with predictions from quantum chromodynamics. The theory has passed many demanding tests: observations of processes involving several jets, the production of heavy quarks, and the way collision probabilities change with energy, all provide evidence that the color charge framework is not just an attractive mathematical story. One particularly important test involves the changing strength of the strong interaction. Because quantum chromodynamics predicts asymptotic freedom, experiments performed at different energy scales should reveal corresponding changes in how strongly quarks interact. They do. Higher energy measurements show the expected weakening of the effective interaction. This gives physicists confidence that the strange distance dependence is real, and not merely a convenient interpretation. Yet the same theory becomes much harder to calculate directly when the interaction grows strong at larger distances. This is why confinement is difficult to handle with simple calculation methods. At high energies and short distances, the weaker interaction allows physicists to use approximation techniques effectively. At lower energies, where quarks are bound into hadrons, the interaction becomes so strong that these methods break down. To study that region, physicists often use computational techniques such as lattice quantum chromodynamics. Instead of trying to solve every aspect of the continuous theory directly, researchers represent space and time on a computational grid and calculate how quarks and gluons behave across that lattice. Powerful computers can then estimate properties of hadrons and other strongly interacting systems. These calculations have become remarkably successful at reproducing measured particle masses and other quantities. It is rather satisfying that one of the strongest interactions in nature requires some of the strongest computers humans can build to understand it properly. The proton sitting quietly inside a glass of water may not look like something that needs a computing center, but appearances continue to be unreliable. Color charge also plays an important role in extreme states of matter such as quark-gluon plasma. Under ordinary conditions, confinement keeps color charge packaged inside hadrons. At sufficiently high temperature and density, however, matter can enter a state where quarks and gluons are no longer bound into individual protons and neutrons in the familiar way. The colour charges are still interacting strongly, but the organisation of the matter changes. This state existed naturally in the early universe, when everything was far too hot for protons and neutrons to survive as separate stable particles. As the universe cooled, quarks became confined into colour-neutral hadrons. In modern laboratories, collisions between heavy nuclei can briefly recreate conditions hot enough to produce quark-gluon plasma. The resulting droplet exists for only an extremely short time before cooling and forming ordinary hadrons again. Studying these collisions helps physicists learn how colour charge behaves when huge numbers of quarks and gluons interact collectively. The plasma does not behave as a simple cloud of independent particles. It shows strong collective motion and acts remarkably like a very low viscosity fluid. Even in a state where ordinary hadrons have temporarily lost their usual identities, the strong interaction remains deeply important. Colour charge may therefore be invisible, but it is responsible for organising matter at several levels. It determines how quarks interact through gluons. It requires ordinary hadrons to be colour neutral. It contributes to confinement. It helps explain why free quarks are not observed. It shapes high-energy collisions and the properties of quark-gluon plasma. Most importantly for ordinary matter, it makes the existence of stable protons and neutrons possible. There is also something curious about the fact that the strongest force in nature is so carefully hidden. Gravity announces itself across entire galaxies. Electromagnetism fills the world with light, chemistry, sparks, magnets, and static shocks received at exactly the moment you were hoping to appear composed. The strong interaction hides its charge inside colour-neutral particles. Its direct effects rarely escape beyond the size of a proton. You can live an entire life without consciously noticing it, even though nearly every atom in your body depends on the structures it creates. The hiding is not accidental in the casual sense. It is built into the rules of confinement and colour neutrality. Observable particles organise themselves so that exposed colour charge does not remain free at ordinary energies. If a high-energy collision produces a quark moving away from the interaction point, the strong field creates new particles before that quark can appear alone. The detector sees a jet of colour-neutral hadrons rather than a single-coloured quark. This makes colour charge unlike any ordinary property we encounter at human scales. You cannot collect a jar of red colour charge and another jar of green colour charge, combine them, and see what happens. You cannot switch off the other interactions and observe colour directly. Everything we know about it comes from the behaviour of particles and the success of the theory describing those behaviours, and yet that hidden property is more than enough to shape the material universe. The proton survives because its quarks form the appropriate colour state. The neutron does the same. Nuclei exist because residual strong effects remain between those colour-neutral particles. Atoms then form around nuclei. Chemistry becomes possible. Matter builds upward from a quantum rule involving a type of charge that nobody can see, and that was given the name colour largely because physicists needed 3 labels and had already used plenty of other words. The deeper consequence of this strange charge becomes most obvious when we try the one thing that seems reasonable whenever particles are bound together. We try to pull them apart. With ordinary forces, enough energy can usually separate the objects involved. A magnet can be pulled away from another magnet. A satellite can escape a planet if it moves fast enough. An electron can be removed from an atom if enough energy is supplied. Quarks do not cooperate with this familiar logic. As their separation increases, the colour field does not simply fade until the quarks are free. The interaction becomes more significant. The stored energy increases, and eventually nature uses that energy to create more quarks. The harder we try to isolate one, the more efficiently the strong interaction finds a way to keep colour hidden inside new neutral combinations. That peculiar refusal to let quarks escape is where colour charge stops being merely an unusual label and becomes one of the strangest forms of confinement anywhere in physics. Trying to separate two quarks sounds, at first, like the sort of experiment that should have a very straightforward ending. If two things are bound together, then surely enough energy should eventually pull them apart. We see versions of this all the time. A satellite can escape a planet if it is given enough speed. An electron can be removed from an atom if enough energy is supplied. Two magnets can be pulled away from each other, even if one of them makes a determined attempt to take your fingertip along for the journey. Bonds can be broken, objects can be separated, and forces can usually be overcome if we are willing to provide enough energy. Quarks are where this comfortable intuition begins to fail. The strong interaction does not simply hold quarks together very tightly. It changes its behavior as we try to separate them, and the result is something far stranger than a particularly strong version of ordinary attraction. The more energy we invest in pulling quarks apart, the more the strong field resists the separation, until the system finds a way to turn that extra energy into new particles. Instead of producing an isolated quark, we end up producing more strongly interacting matter. This is confinement, and it is one of the reasons the world around us is made from protons, neutrons, and other composite particles rather than loose collections of quarks drifting freely through space. The easiest way to approach confinement is to begin with what happens at very short distances. When quarks are extremely close together, the effective strong interaction between them becomes weaker. This is the behavior known as asymptotic freedom. It means that inside a proton, when we probe the quarks over sufficiently short distances and at sufficiently high energies, they can behave almost as though they are moving independently. This was an important clue in the development of the modern theory of the strong interaction, because experiments showed that protons contained small constituents that seemed surprisingly free when struck by energetic particles. If quarks were supposed to be held together by the strongest interaction in nature, their apparent freedom looked puzzling. Quantum chromodynamics resolved the problem by showing that strong does not mean equally strong at every distance. The effective interaction changes with scale. Very close together, quarks can behave relatively freely. Try to move them farther apart and the situation reverses. This already makes the strong interaction unusual. With gravity, increasing the distance weakens the attraction. The same general idea applies to the familiar electrical attraction between opposite charges. Move the objects farther apart and the force becomes smaller. Eventually, at a sufficiently large distance, the interaction may become so weak that we can practically ignore it. Quarks do not give us this convenient escape route. As their separation increases, the effect of the strong interaction becomes more significant. The color field between them stores more energy, and pulling farther requires even more work. The interaction does not relax simply because the particles are moving apart. A useful mental picture is to imagine stretching a flexible cord. When the ends are close together, the cord is relaxed. Pull them apart and the tension grows. Continue pulling and more energy is stored in the stretched cord. This captures one important feature of quark confinement, but the analogy must be handled carefully because an ordinary cord eventually snaps. If you pull hard enough, you get two separate pieces. The strong field behaves differently. When enough energy accumulates, nature can use that energy to create a new quark and antiquark pair. The original system then reorganizes into new color neutral particles. What looked like an attempt to produce one free quark at each end has instead produced additional hadrons. Suppose, in a simplified picture, that we begin with a quark and an antiquark bound together inside a meson. We try to separate them. The energy in the strong field increases as the distance grows. Eventually it becomes energetically favourable to create another quark and antiquark pair from the energy we have supplied. One of the new particles combines with the original quark, while the other combines with the original antiquark. We started with one meson and ended with two mesons. At no stage do we obtain a single free quark waiting patiently for us to measure it. The strong interaction has effectively responded to our attempt at separation by creating another set of partners. This does not mean quarks are literally aware that someone is trying to isolate them. Tempting though that interpretation may become after several hours in a particle physics laboratory. It is simply what follows from the behaviour of the quantum fields and the available energy. The strong interaction permits the creation of new quark and antiquark pairs when enough energy is concentrated in the system. Confinement is therefore not like putting a quark inside an unbreakable physical box. There is no hard wall surrounding the particle. Instead, the structure of the strong field prevents a lone colour-charged quark from appearing as an ordinary isolated particle. This is why particle accelerators do not simply smash protons open and release their quarks like seeds from a fruit. When high-energy collisions produce energetic quarks or gluons, those colour-charged objects begin moving away from the collision point, but they cannot remain isolated. The growing strong field leads to the creation of additional quarks and antiquarks. These new particles combine into colour-neutral hadrons. By the time the products travel far enough to pass through the detector, the original quark or gluon has become associated with a spray of new particles, moving in roughly the same direction. Physicists call these sprays jets. Jets are one of the main ways we study quarks and gluons experimentally. A detector does not record a free quark directly. It records the hadrons produced after the strong interaction has reorganized the colour-charged particles into allowed combinations. By measuring the energies and directions of those hadrons, researchers can reconstruct information about the quark or gluon that initiated the jet. This is a little like trying to learn about a firework by examining the pattern of sparks after it explodes, except that the sparks themselves are complicated composite particles, and the firework is smaller than an atomic nucleus. The details become challenging, but the overall principle is clear. Confinement hides quarks from direct observation, while still leaving patterns that reveal their presence. The fact that quarks cannot normally be isolated also explains why fractional electric charges are never seen wandering around in ordinary matter. Up quarks and down quarks carry electric charges that are fractions of the familiar amount associated with protons and electrons. Yet every free particle we commonly observe has an electric charge that combines into familiar whole units. Confinement is a major reason for this. Quarks remain grouped inside hadrons, and the electric charges of the quarks combine to produce the total charges of those larger particles. A proton ends up positively charged. A neutron ends up electrically neutral. Mesons have their own allowed totals. The unusual fractional charges remain buried inside composite particles. Confinement is closely connected to colour charge, which is why the previous discussion of red, green, blue, and their corresponding anticolours matters so much. The observable particles around us are colour neutral. 3 quarks can combine into a colour-neutral baryon. A quark and antiquark can combine into a colour-neutral meson. The strong interaction continually rearranges colour through gluon exchanges, but the complete hadron remains neutral overall. A single quark would carry exposed colour charge, and the dynamics of quantum chromodynamics do not allow such an object to appear freely at ordinary energies. This creates a striking contrast with the electric charge. An isolated electron can exist quite happily. It carries electric charge and can move through space without being forced to find a positively charged partner. A proton can also exist by itself, carrying positive electric charge. We can build beams of electrons or protons and send them through accelerators. Colour charge does not behave this way. We cannot build a beam consisting of isolated red quarks, adjust a few magnets, and send it around a laboratory. Any attempt to produce such a colour-charged object results in hadron formation before it can travel freely over macroscopic distances. The mathematical reason for this difference lies partly in the fact that gluons interact with one another. Photons, the carriers of electromagnetism, do not carry ordinary electric charge. Gluons carry strong colour information and therefore participate in the interaction they transmit. This self-interaction changes the structure of the strong field. Instead of spreading outward in the same way as an ordinary electric field, the colour field between separated quarks tends to become concentrated. The result is often pictured as a narrow tube of strong field connecting the colour charges. As the quarks are separated, this tube becomes longer and stores more energy. The energy does not simply spread harmlessly across a larger volume and fade away. That is why the cost of separation continues increasing. At some point, the accumulated energy is sufficient to create new matter, and the system breaks into new colour-neutral combinations rather than exposing isolated colour charge. In this sense, the strong interaction behaves almost as though the field itself prefers to reorganize matter before allowing a quark to escape. There is an important subtlety here. Saying that quarks can never escape is a useful description of confinement under ordinary conditions, but it does not mean quarks are always permanently locked inside one particular proton or neutron. High-energy processes can destroy a proton, create new hadrons, transform particles, and produce conditions where the familiar boundaries between individual protons and neutrons temporarily disappear. Quarks can change which composite particles they belong to. What confinement prevents is the appearance of an isolated colour-charged quark travelling freely through ordinary space. This becomes especially interesting when we consider quark-gluon plasma. At extremely high temperatures and densities, matter can enter a state where quarks and gluons are no longer confined into individual protons and neutrons in the familiar way. Such conditions existed in the early universe, and can be recreated for extremely brief periods in collisions between heavy atomic nuclei. It might sound as though this means confinement has simply disappeared and free quarks have finally escaped, but even here the description requires care. The quarks and gluons remain part of a strongly interacting collective system. They are not isolated particles travelling independently through empty space. As the plasma cools, they form hadrons again before reaching ordinary detectors. The early universe provides a useful way to appreciate how confinement shaped matter. Shortly after the beginning of cosmic expansion, temperatures were so high that stable protons and neutrons could not exist in their familiar forms. Quarks and gluons were part of an extremely hot interacting state. As the universe expanded and cooled, the conditions changed. The strong interaction organized quarks into colour-neutral hadrons. Protons and neutrons became stable building blocks. Those particles later participated in the formation of atomic nuclei. Much later, electrons became associated with nuclei to form neutral atoms. Stars, planets, chemistry, and everything familiar followed from there. Confinement was therefore part of the process that transformed an early universe, filled with extremely energetic particle interactions, into a universe containing stable matter. The quarks did not vanish when protons and neutrons formed. They became locked inside those particles in colour-neutral combinations. Every proton in your body carries the result of that transition. The quarks inside it have remained confined while the proton may have passed through stars, interstellar gas, planetary material, oceans, food, and whatever complicated sequence eventually brought it into you. The proton can travel enormous distances through cosmic history while its internal quarks remain unavailable as separate objects. This stability raises another question. If the strong interaction stores more energy when quarks are separated, why do the quarks inside a proton not simply collapse into one point, where their separation is as small as possible? Quantum mechanics prevents such a simple outcome. Quarks are quantum particles, and their behavior is governed by a combination of motion, uncertainty, field energy, and interaction effects. Squeezing a quantum system into an arbitrarily tiny region changes its energy. The proton settles into a stable quantum state where the competing contributions balance. It is not a miniature bag containing 3 stationary quarks attached by strings. The quarks, gluons, and surrounding quantum activity together form a stable, strongly interacting system. This is also why the size of a proton is not determined by a little physical shell surrounding it. There is no hard surface in the ordinary sense. The proton has a characteristic spatial extent arising from the distribution of its internal fields and constituents. When high-energy particles scatter from a proton, they probe different aspects of that structure. At lower energies, the proton can appear more like a single composite object. At higher energies and shorter distances, the internal quarks and gluons become visible through the scattering patterns. The object we call a proton therefore depends somewhat on the scale at which we examine it. Confinement also makes calculating the properties of protons and neutrons much more difficult than simply adding together the properties of three quarks. At short distances, where the strong interaction becomes weaker, physicists can use certain approximation techniques with considerable success. At the larger internal distances associated with confinement, however, the interaction is too strong for those simple methods to work reliably. The gluons interact with each other, the quarks interact with the gluons, additional quark and antiquark activity contributes, and the entire system becomes strongly coupled. This is where lattice quantum chromodynamics becomes important. Physicists can represent space and time as a computational grid and calculate the behavior of the strong fields across that lattice. These calculations require substantial computing power, but they allow researchers to estimate properties such as the masses of hadrons and the behavior of strongly interacting matter. The agreement between these calculations and experimental measurements provides powerful evidence that quantum chromodynamics really does describe the underlying physics. One of the remarkable outcomes is the explanation of where most of the proton's mass comes from. The individual masses of the valence quarks make up only a small fraction of the total proton mass. Much of the rest arises from the energy of the quark and gluon system. The strong interaction that confines the quarks therefore contributes enormously to the mass of ordinary matter. Confinement is not merely preventing particles from escaping, it is part of what gives protons and neutrons the mass they possess. This makes the interior of ordinary matter far more energetic than its calm appearance suggests. Put a stone on a desk and it seems completely inactive. Inside the stone are atoms. Inside their nuclei are protons and neutrons. Inside those particles, quarks and gluons form strongly interacting quantum systems, whose field energy contributes most of the nuclear mass. None of this causes the stone to shake visibly, because the internal systems are stable. A stable system can contain enormous amounts of internal activity without changing its overall identity. The same principle appears throughout physics. A stable star contains constant nuclear reactions. A stable atom contains quantum electrons that are not motionless little planets. A stable proton contains quarks and gluons in a complicated, strongly interacting state. Stability does not mean inactivity. It means that the complete arrangement persists. Experimental evidence for confinement appears every time high-energy quarks produce jets instead of isolated quark tracks. Particle detectors are extremely good at identifying charged particles moving through their layers. If free quarks existed and carried their expected fractional electric charges, they would leave very unusual signatures. Searches for such objects have been performed, but none has been found as a freely propagating particle. The evidence instead supports the picture that quarks remain confined inside color-neutral hadrons. Physicists have also studied how jets develop. An energetic quark can radiate gluons. Those gluons can produce further activity, creating a cascade before the final process of hadron formation. This makes the path from one high-energy quark to a detector full of ordinary particles surprisingly complicated. Researchers use detailed theoretical models and computer simulations to predict these patterns. By comparing simulated events with real collision data, they test quantum chromodynamics with increasing precision. There is something almost backwards about the experimental situation. In many areas of science, we begin with visible objects and infer the force between them. Here, we know there must be quarks because of the patterns they produce, yet the very interaction we are studying prevents us from ever collecting one by itself. The theory explains why the evidence is indirect. Confinement is both the phenomenon being studied and the reason the objects involved refuse to appear in isolation. It also explains why hadrons dominate the strongly interacting particles observed in nature. Protons and neutrons are the familiar examples, but accelerators have discovered many other baryons and mesons. Some contain strange quarks, charm quarks, or bottom quarks. Others are excited states of more familiar combinations. Most decay rapidly into lighter particles, but while they exist, their quarks remain confined. The strong interaction permits an enormous variety of composite particles, while still refusing to permit the simplest sounding possibility, one quark on its own. There are even more unusual hadrons containing arrangements beyond the traditional three quarks of a baryon, or the quark and antiquark pair of a meson. Experiments have discovered particles interpreted as tetraquarks and pentaquarks, involving 4 and 5 quark constituents in their overall descriptions. These discoveries show that colour neutrality can be achieved through more complicated combinations. Confinement does not demand that nature use only the most familiar packages. It demands that the complete observable state satisfy the rules of colour. These exotic particles are useful because they test how well physicists understand strong interaction binding. Some may behave like tightly connected multiquark systems, while others may resemble loosely bound combinations of ordinary hadrons. Distinguishing between these possibilities is an active area of research. The underlying theory is known, but strongly interacting systems can produce rich behaviour that is difficult to predict from first principles. That is one of the recurring themes of the strong interaction. The basic rules can be written down compactly by physicists, yet the consequences are enormously complex. A proton is one example, an atomic nucleus is another, quark-gluon plasma is another still. The difficulty does not come from ignorance of which fundamental interaction is responsible. It comes from the large number of strongly interacting components and the fact that gluons participate in the force themselves. Confinement also helps explain why the strong interaction, despite being the strongest fundamental interaction, remains hidden from daily experience. All the colour charge in ordinary matter is confined inside colour-neutral particles. Those particles then form nuclei, and the direct colour interaction does not extend outward over ordinary distances. The fundamental force effectively locks itself away inside the matter it creates. What reaches beyond individual protons and neutrons is only a residual effect. That residual effect is much weaker than the fundamental interaction between quarks, but it's still powerful enough at nuclear distances to bind protons and neutrons together. This is where confinement leads naturally back to the atomic nucleus. A proton may be colour neutral overall, but its internal quarks and gluons do not become irrelevant simply because the net colour charge is hidden. The strong field inside one nucleon can produce leftover interactions with another nucleon nearby. Somewhat as neutral atoms can still exert electromagnetic attractions on one another because of their internal charge structure. The comparison is imperfect, but it gives the right direction. A colour-neutral proton is not a blank object with no strong physics inside it. It is an active composite system. Bring another proton or neutron close enough, and their internal strong dynamics can create an effective attraction. This attraction operates over only a short nuclear distance, which is why it can bind neighbouring nucleons without reaching across atoms or everyday objects. And this leftover force is responsible for one of the most important compromises in nature. Protons electrically repel each other, yet nuclei containing many protons can remain intact because the residual strong force dominates when nucleons are close enough. Neutrons contribute to this binding without adding positive electric charge. The balance between nuclear attraction and electrical repulsion determines which nuclei can exist, which are unstable, and how nuclear reactions release energy. So confinement does something slightly unexpected. It hides the fundamental strong interaction inside protons and neutrons, but it does not erase its influence. The full colour force keeps quarks from escaping, while a weaker remnant reaches just far enough beyond each nucleon to help assemble the atomic nucleus. That remnant is the reason the strong interaction can remain invisible in ordinary life, while still holding together the centres of nearly every atom around us, and it is there, in the small amount of strong influence that leaks beyond colour-neutral particles, that the next part of the story begins. Once quarks are locked safely inside protons and neutrons, the strong interaction has not quite finished its work. The colour charge of the quarks is hidden inside particles that are colour neutral overall, so the fundamental strong force does not simply reach outward from a proton and grab another proton across ordinary distances. If it did, matter would behave very differently. Your hand might become permanently attached to a table every time the nuclei inside the two objects came vaguely near one another, which would make breakfast inconvenient and furniture shopping surprisingly dangerous. Instead, almost all of the fundamental colour interaction remains confined inside protons and neutrons. But not absolutely all of its influence disappears. A weaker leftover effect extends just beyond those particles over an extremely short distance. This is the residual strong force, and it is powerful enough to bind neighbouring protons and neutrons together inside atomic nuclei. The relationship is somewhat like the leftover electromagnetic attraction that can exist between electrically neutral atoms. An atom can contain equal positive and negative electric charge and therefore appear neutral overall, yet the arrangement of those charges can still allow weak attractions between neighbouring atoms. Protons and neutrons are colour neutral in a much deeper quantum sense, but the strong dynamics inside them leave behind an effective interaction. That remaining attraction is the reason a nucleus containing several protons does not immediately fly apart under electrical repulsion. This distinction is worth keeping clear because the phrase strong force is often used for two closely related things. At the deepest level, there is the fundamental strong interaction between quarks and gluons, described by quantum chromodynamics. That interaction confines quarks inside hadrons such as protons and neutrons. At the level of the atomic nucleus, there is the residual strong interaction between the protons and neutrons themselves. The second one is a consequence of the first, rather than an entirely separate fundamental force. If the strong interaction between quarks is the machinery inside a building, the residual nuclear force is more like a vibration that can still be felt through the wall. The vibration is weaker than the machinery producing it, but if you are standing close enough, it can still be very noticeable. In the nucleus, close enough means extraordinarily close. Protons and neutrons have to be separated by distances comparable with their own size before this residual attraction becomes important. At greater distances it fades rapidly, which is why neighbouring atoms do not usually start exchanging nuclear particles across the room. The short range of the residual force solves one problem while creating another interesting one. It solves the problem of how nuclei can hold together without making all matter collapse into one enormous nuclear object. If the nuclear attraction had the reach of gravity, every proton and neutron might attract vast numbers of others over large distances. Instead, each nucleon, which is the general term for either a proton or neutron, mainly interacts strongly with nearby nucleons. This gives nuclear matter a kind of local character. A nucleon near the centre of a nucleus can be strongly influenced by several neighbours, while one at the surface has fewer nearby particles to interact with. Adding more nucleons therefore tends to make the nucleus larger, rather than giving each existing nucleon an equally strong attraction to every new arrival. The strong nuclear force is extremely powerful at close range, but it does not provide an unlimited amount of binding merely because more particles are added. Electromagnetism behaves differently. Every proton in the nucleus carries positive electric charge, and every other proton repels it. The electrical interaction reaches across the entire nucleus. As the number of protons increases, this repulsion becomes increasingly significant. The nuclear attraction remains mostly local, while electrical repulsion builds throughout the system. This competition explains much of the pattern we see among atomic nuclei. Small nuclei can remain stable with roughly similar numbers of protons and neutrons. As nuclei grow larger, extra neutrons become increasingly valuable because neutrons participate in the residual strong attraction without adding positive electric charge. They contribute to nuclear binding without increasing proton-to-proton repulsion. This is why many heavy stable nuclei contain noticeably more neutrons than protons. Nature has found that if you're going to pack a large number of positive charges into a very small space, bringing along some electrically neutral participants is generally a good idea. It would still be misleading to think of neutrons as simple glue particles placed between pairs of protons. The nucleus is a quantum system, and the nucleons do not occupy fixed seats. Their behavior depends on quantum states, their motion, their spin, their interactions, and the fact that protons and neutrons are fermions. Identical fermions obey a rule that prevents them from all occupying exactly the same quantum state. This produces a structured set of allowed nuclear states and helps prevent all the nucleons from simply collapsing into one identical condition. The nucleus has internal organization, even though it is far too small to resemble anything familiar. It can possess shells of quantum states, collective vibrations, rotations, and deformations. The residual strong force provides much of the attraction, but quantum mechanics determines how the particles can actually arrange themselves while experiencing that attraction. At ordinary nuclear distances, the effective interaction between nucleons is attractive, but if the particles are pushed extremely close together, the interaction becomes strongly resistant to further compression. This is another important detail because a force that were purely attractive at all distances might allow nuclear matter to collapse inward indefinitely. Instead, the nuclear interaction has a more complicated distance dependence. There is an attractive region that allows nucleons to bind, along with a short distance repulsive behavior that helps establish a typical spacing. Nuclear matter is therefore extremely dense but not infinitely compressible. Protons and neutrons remain packed together in a characteristic arrangement rather than piling into exactly the same location. This property helps explain why many atomic nuclei have roughly similar internal densities. A heavier nucleus generally contains more nucleons and occupies a larger volume, but its central density does not simply increase without limit as nucleons are added. Each nucleon mostly interacts with a limited set of nearby neighbours, and the short-distance repulsion discourages excessive compression. This is sometimes described as a saturation property of nuclear forces. Once a nucleon is surrounded by nearby partners, adding more particles elsewhere in the nucleus does not multiply its binding indefinitely. The result resembles a liquid drop in some useful ways. Add more water to a drop and the drop becomes larger rather than every water molecule being crushed into a smaller and smaller region. A nucleus is not literally a liquid drop, but the comparison becomes surprisingly helpful when considering its overall behavior. The liquid drop model was historically important because it captured several broad features of nuclei without requiring every nucleon to be followed individually. A nucleus has something like a surface, because nucleons near the outside have fewer neighbours and therefore experience less binding than nucleons deep inside. Electrical repulsion between protons pushes in the opposite direction, especially in larger nuclei. These competing effects help determine whether a particular nucleus is stable and how it might respond if disturbed. A heavy nucleus can deform, stretching away from a roughly spherical shape. If the deformation becomes large enough, the short-range attraction may no longer be able to hold the entire object together against the electrical repulsion between its separated regions. The nucleus can then split into smaller pieces. This process is nuclear fission. Fission gives us a dramatic example of how the residual strong force and electromagnetism compete. In a very heavy nucleus, the strong nuclear attraction binds neighbouring nucleons together, but the many protons also create substantial electrical repulsion. If the nucleus divides into two smaller nuclei, the protons in those new pieces still repel one another, and the fragments can move apart with considerable energy. The reason energy is available is tied to nuclear binding. Certain medium-sized nuclei are more tightly bound than the very heaviest ones. When a large nucleus splits into more tightly bound products, the difference in energy can appear as motion, radiation, and other forms of released energy. The strong interaction is therefore involved not only in keeping nuclei together, but also in determining how much energy can be released when nuclear structures rearrange. At the opposite end of the nuclear scale, fusion also depends on the same binding behaviour. Light nuclei can sometimes combine into heavier nuclei that are more tightly bound. When that happens, energy can be released. The Sun relies on this process. Hydrogen nuclei in the solar core are positively charged, and therefore repel each other electrically. For fusion to occur, they must approach extremely closely, close enough for nuclear interactions to become significant. The temperature in the solar core gives nuclei substantial motion, but even that is not usually sufficient for them to overcome the electrical barrier through ordinary classical motion alone. Quantum mechanics allows a chance for particles to pass through barriers they could not classically cross, a phenomenon called tunneling. When the nuclei manage to reach nuclear distances, the residual strong force can become dominant, and new, bound nuclear states can form. The complete chain of solar fusion involves more than the strong interaction. The weak interaction plays an essential role in converting particles during early steps, while electromagnetism creates the electrical barrier, and gravity creates the immense pressure and temperature of the stellar core. The strong interaction determines much of the nuclear binding involved in the resulting structures. A star is therefore not powered by one force acting alone. It is more like a complicated agreement among several fundamental interactions, each contributing something different. Gravity gathers the material, electromagnetism keeps charged nuclei from approaching too easily, quantum mechanics provides a route through the barrier, the weak interaction changes particle identities where required, and nuclear binding makes the resulting reactions energetically important. Considering how peaceful sunlight feels on a quiet morning, the underlying arrangement is remarkably busy. The amount of binding in a nucleus can be understood through the energy needed to take it apart. A nucleus that is strongly bound requires substantial energy to separate into individual protons and neutrons. When those particles first come together into a bound state, energy is released. This means the complete nucleus has less total mass than the sum of its separated nucleons would have. The difference corresponds to the binding energy. Nothing has gone missing. The system simply contains less internal energy once it is bound, and that change appears in its total mass. This is one reason nuclear processes can release far more energy per particle than ordinary chemical reactions. Chemistry mainly rearranges electrons and electromagnetic bonds between atoms. Nuclear reactions rearrange the structures governed by nuclear binding, where the relevant energy changes are much larger. The pattern of binding across different nuclei is especially important. Very light nuclei can often become more tightly bound by joining together, which is why fusion releases energy in stars. Very heavy nuclei can sometimes become more tightly bound by splitting, which is why fission can release energy. Between those extremes are nuclei with particularly strong binding per nucleon. Iron and neighbouring elements lie near this region, which is one reason the nuclear burning stages of massive stars eventually run into difficulty as they build heavier and heavier nuclei. Fusion that produces elements approaching this region can release energy, but continuing beyond it no longer offers the same advantage. A massive star that has spent millions of years using nuclear reactions to help support itself against gravity can eventually reach a point where those reactions can no longer provide what the core needs. When that happens in a sufficiently massive star, the consequences can be enormous. The core can collapse under gravity, driving matter to extraordinary densities. Atomic structures are destroyed. Electrons and protons participate in reactions that produce neutrons and neutrinos, and conditions become so extreme that our familiar picture of separate nuclei begins to change. The outer layers of the star may be blasted into space in a supernova. During these violent events, and during collisions involving neutron stars, heavy nuclei can form through rapid processes involving large numbers of neutrons. Many of the elements heavier than iron owe their cosmic abundance to such environments. The gold in a ring and the iodine used by the human body therefore depend indirectly on nuclear binding rules set by strong interaction physics. The existence of stable nuclei also depends on a delicate relationship between the number of protons and neutrons. If a nucleus contains too many neutrons relative to protons, it may be unstable and transform through radioactive decay. If it contains too many protons, electrical repulsion and other nuclear effects can also make it unstable. The weak interaction can convert a neutron into a proton or a proton into a neutron through certain decay processes, moving the nucleus toward a more favourable balance. This produces the landscape of isotopes found throughout nuclear physics. An element is defined by its number of protons, but different isotopes of that element contain different numbers of neutrons. Some isotopes are stable, others decay rapidly. Some have half-lived so long that they survive naturally over the age of Earth. These differences are not arbitrary. They reflect the nuclear energy structure created by the residual strong force, electromagnetism, and quantum mechanics. Add one neutron to a nucleus and the result may become more stable. Add another and the result may become less stable. Certain numbers of protons or neutrons produce particularly favourable shell arrangements. These are the so-called magic numbers mentioned earlier. Nuclei with filled nuclear shells can be unusually stable, showing once again that nuclear matter is not simply a sticky collection of particles. The nucleons occupy quantum states with structure, and their arrangement can matter almost as much as their total number. Researchers study increasingly unusual isotopes to learn how the residual strong force behaves when nuclear matter is pushed away from the stable combinations found naturally on Earth. Some experimental nuclei contain far more neutrons than ordinary stable matter. Others are extremely rich in protons. Many survive only briefly before decaying. By measuring their masses, lifetimes, decay products, and internal states, physicists test models of nuclear interactions. These exotic nuclei are useful precisely because they force our theories into conditions where the balance of forces becomes unusual. A model that works nicely for common carbon or oxygen nuclei may encounter a much harder test when presented with a short-lived nucleus that contains an awkward number of neutrons and seems determined to disappear before the detector has finished introducing itself. There are boundaries beyond which an additional proton or neutron simply cannot remain bound. These are known as the proton and neutron drip lines. Near such a boundary, adding one more nucleon can produce a system that immediately releases that particle again. Studying these limits helps reveal the reach and structure of the nuclear force. It also matters for astrophysics because environments such as stellar explosions can produce extremely neutron-rich nuclei, far from the stable combinations commonly found on Earth. Understanding their behaviour is essential if physicists want to reconstruct how heavy elements are assembled in the cosmos. The residual strong force can also create loose bound states that show how little energy may separate stability from instability. The simplest bound nuclear system containing both a proton and a neutron is the deuteron, the nucleus of heavy hydrogen. It consists of one proton and one neutron. This pair is bound, but not with anything like the overwhelming strength someone might expect from hearing the phrase strongest force in the universe. The reason is that we're no longer dealing with the full colour interaction between individual quarks. We are looking at its residual effect between two colour neutral composite particles. The deuteron sits close enough to the edge of binding that small changes in the underlying nuclear interaction could alter whether it exists at all. That fact has consequences for stars because deuterium participates in nuclear reactions. The detailed strengths of nuclear forces influence which reaction pathways are available and how readily different nuclei can form. If the residual interaction were substantially weaker, some nuclei important for stellar fusion and cosmic element formation might not bind. If it were substantially stronger, other nuclear arrangements might become possible, changing the balance of elements. The universe, we observe, depends on the actual values of these interactions, not merely on the fact that the forces exist. The residual strong force is also responsible for an interesting reversal at very short distances. As nucleons approach one another, attraction initially becomes important, but if they are forced too close, the effective interaction develops a strong repulsive component. This behavior is important inside dense nuclear matter because it resists compression. The exact origin of this short-range behavior is connected to the complicated quark structure of the nucleons and the way quantum interactions operate between them. Nuclear physicists can describe it using effective models, but deriving every detail directly from the underlying quark and gluon theory remains difficult. That difficulty is a recurring theme. Quantum chromodynamics is the fundamental theory, but protons and neutrons are complicated composite objects, and their interactions at nuclear distances occur where the strong force is not weak enough for the easiest approximation methods. Physicists therefore use several approaches. Some work with effective theories that describe nucleons and mesons without tracking every quark explicitly. Others use large numerical calculations based on the fundamental theory. Nuclear models can focus on shells, collective motion, clusters, or many body interactions depending on the problem being studied. These different approaches are not signs that physics has no idea what is going on. They reflect the fact that a many-particle quantum system can be described usefully at several levels. This is similar to the way weather can be studied without following the quantum state of every molecule in the atmosphere. Knowing that air is made from molecules does not mean every useful weather forecast should begin by calculating individual molecular collisions. Nuclear physics often works in the same layered way. Quarks and gluons provide the deeper foundation, but for many nuclear questions, protons and neutrons are the practical objects to describe. The challenge is building an effective description that preserves the important consequences of the underlying strong interaction. The connection becomes even more demanding inside neutron stars. These objects compress enormous amounts of matter into a region only about the size of a city. The densities become comparable with, and in the deepest regions may exceed, the density found inside atomic nuclei. Under such conditions, the residual interactions among nucleons help determine how the matter responds to pressure. If nuclear matter is relatively easy to compress, a neutron star of a given mass can be smaller. If it resists compression more strongly, the star can be larger. The relationship between pressure and density is called the equation of state, and determining it for extremely dense nuclear matter is one of the major problems connecting nuclear physics with astronomy. Observations of neutron stars provide clues. Their masses can be measured in binary systems. Their sizes can be constrained through observations of radiation. When two neutron stars spiral together and collide, gravitational waves reveal information about how easily the stars deform in each other's gravity before merging. That deformation depends on the properties of the dense matter inside them, which in turn depend on nuclear interactions rooted in the strong force. So an observatory listening to changes in space caused by two colliding stars can indirectly test physics originating inside protons and neutrons. The strongest interaction at microscopic scales becomes part of the behavior of some of the densest astronomical objects in the universe. There may also be forms of matter inside neutron stars that go beyond familiar protons and neutrons. At sufficiently high density, new particles containing strange quarks might appear, or nucleons may overlap enough that describing them as separate objects becomes less useful. Some models consider states where quarks themselves play a more direct role. Scientists do not yet know exactly which of these possibilities, if any, occur in nature. The answer depends heavily on strong interaction physics under conditions that are difficult to reproduce experimentally. Neutron stars therefore serve as natural laboratories, operating at pressures no human-built device can sustain. For ordinary matter, however, the residual strong force performs a quieter task. It allows nuclei to survive. Every stable carbon nucleus, every oxygen nucleus in the air, and every calcium nucleus in bone exists because close-range nuclear attraction is strong enough to overcome the competing effects within that particular arrangement. That statement can sound almost too ordinary after discussing supernovae and neutron stars, but it is the essential point. The universe does not need a force to be dramatic in order for it to be important. Sometimes the important achievement is simply keeping a nucleus intact for several billion years. The residual force also reminds us that the boundaries between forces and particles become less obvious at the quantum level. In everyday language, we often imagine two objects first, and then imagine a force acting between them. In quantum field theory, the particles and interactions are parts of the same underlying framework. Protons and neutrons are already products of the strong interaction before they ever begin interacting with one another inside a nucleus. The residual force between them is therefore an interaction between composite systems whose very existence depends on the deeper force responsible for their internal structure. This is why the phrase nuclear glue is both useful and slightly dangerous. It captures the idea that something binds the nucleus, but ordinary glue is a separate material applied between two objects that existed perfectly well beforehand. The strong interaction is more fundamental than that. It helps create the protons and neutrons themselves, and then leaves behind enough residual interaction for those particles to form nuclei. It helps make the pieces, and then helps the pieces assemble. Once nuclei exist, the consequences spread outward through almost every level of ordinary matter. Electrons can organize around stable nuclei. Atoms gain their identities from the number of protons they contain. Chemistry follows from electron behavior around those nuclear centers. Molecules form, materials emerge, stars process nuclei into new elements, planets inherit those elements. Biology eventually makes enthusiastic use of carbon, oxygen, nitrogen, phosphorus, calcium, iron, and many others. The residual strong force does not participate directly in a chemical bond inside a strand of biological material, but the nuclei required for that chemistry would not exist without it. And yet under sufficiently violent conditions, the calm nuclear arrangement can be disrupted. Heat a system enough, compress it enough, collide nuclei hard enough, or place matter inside a collapsing star, a nuclear structure can give way to more extreme states. Protons and neutrons can be rearranged, nuclei can fuse or split, and at still higher energies even the usual boundaries of nucleons can become less meaningful. The residual force that quietly binds ordinary nuclei is therefore also the doorway towards some of the most energetic processes in nature, where nuclear matter is transformed on enormous scales, and the strong interaction becomes visible not through a single proton or neutron, but through exploding stars, dense stellar remnants, and conditions approaching those that filled the early universe. The strong interaction spends most of its existence hidden inside matter, doing work on scales so small that even an atom is far too large to give us an intuitive picture of what is happening. Yet there are places in the universe where gravity squeezes matter so hard, temperatures rise so high, and nuclei are pushed through such violent changes that strong interaction physics begins to influence the behavior of entire stars. This does not mean the strong force suddenly escapes from atomic nuclei and reaches across space. Its range remains tiny. What changes is the amount of matter being forced into conditions where nuclear distances matter. When trillions upon trillions of nuclei are fusing, breaking apart, being compressed, or transformed at once, the microscopic rules of nuclear binding can determine what happens to an object larger than a planet. Stars provide the first familiar example. They spend much of their lives in a long competition between gravity pulling inward and pressure resisting that collapse. Nuclear reactions are central to maintaining that pressure because they provide the energy that keeps stellar interiors hot. In this environment, the strong interaction is not working alone, but it determines much of the binding structure of the nuclei involved, deciding which nuclear arrangements can release energy when matter changes from one form to another. Gravity may build the stage, but nuclear physics decides a surprising amount of what the actors are allowed to do. A star such as the Sun begins with hydrogen as its main nuclear fuel. Hydrogen nuclei are positively charged, so electromagnetism makes them repel one another long before the residual strong force can become important. To react, the nuclei must approach to extremely short distances. High temperatures make the particles move rapidly, while quantum tunneling gives them a chance to cross the electrical barrier even when their classical energy would not be sufficient. Once nuclear distances are reached, the strong interaction becomes important and new bound structures can form. The complete process also requires the weak interaction during crucial steps. So saying that stars are powered by the strong force alone would be incorrect. Stellar fusion is a cooperative arrangement involving gravity, electromagnetism, quantum mechanics, the weak interaction, and strong interaction physics. What the strong interaction contributes is the pattern of nuclear binding that allows certain final states to contain less energy than the particles that entered the reaction. That difference can be released and eventually help maintain the hot stellar interior. For a star, this process can continue for an astonishingly long time because nuclear reactions do not consume the available fuel all at once. A star spends most of its life in a relatively stable condition, where inward gravity and outward pressure remain in balance. More massive stars live much faster lives because their central conditions are hotter and their nuclear fuel is processed more rapidly. As the available hydrogen in the core is depleted, the internal structure changes. The core contracts, temperatures rise, and new nuclear reactions can become possible. Helium can participate in reactions that produce carbon, and sufficiently massive stars can eventually proceed through additional stages that involve heavier nuclei. Carbon, oxygen, neon, magnesium, silicon, and other elements become part of an increasingly complicated sequence. The details differ depending on stellar mass and conditions, but the general trend is that each later stage requires hotter and more demanding conditions. The star is effectively exploring the landscape of nuclear binding created by the strong interaction. Some rearrangements release energy and therefore help the star support itself. Others do not. Eventually, that distinction becomes critical. The process cannot continue profitably by fusing heavier nuclei forever. There is a region around iron and nearby nuclei where nuclear binding is especially strong. Once a massive stellar core becomes dominated by nuclei in that neighborhood, further ordinary fusion no longer provides the same source of useful energy. This creates a serious problem because gravity has not taken the evening off. The star still contains an enormous amount of mass pulling inward, but the core can no longer rely on another easy stage of energy, producing fusion to maintain its previous structure. The situation becomes increasingly unstable. Under the rising temperatures, energetic radiation can begin breaking heavy nuclei apart, undoing some of the nuclear assembly that earlier reactions had spent so much time creating. Energy that might otherwise have helped support the core is consumed in those processes. At the same time, electrons can be captured by protons through the weak interaction, producing neutrons and neutrinos and reducing an important source of pressure. Several effects therefore work in the same unfortunate direction. The core begins collapsing rapidly, and the calm life of a massive star turns into one of the most extreme changes matter can experience. During this collapse, the density rises enormously. Atomic structure was already irrelevant in the hot stellar core, but now even the distinction between separate nuclei begins to change as matter is forced toward nuclear density. Protons and electrons participate in reactions that leave the material increasingly rich in neutrons, while huge numbers of neutrinos are produced. For a while, many neutrinos can escape, but as the density continues rising, even particles famous for passing almost effortlessly through ordinary matter begin interacting often enough to become temporarily trapped within the collapsing region. The inner core compresses until the behavior of nuclear matter becomes crucial. At these densities, the strong interaction and quantum effects resist further compression. The nuclear equation of state, meaning the relationship between the density, pressure, temperature, and composition of the material, becomes one of the key pieces of physics determining how the collapse proceeds. Researchers study equations of state precisely because matter in supernova cores, neutron stars, and neutron star mergers spans conditions where nuclei, nucleons, and possibly more exotic, strongly interacting forms of matter can all become relevant. The collapsing inner core can stiffen when nuclear densities are reached, causing the inward motion to slow dramatically and producing what is often called core bounce. A shock wave forms and begins moving outward through the infalling material. It might seem that the problem is solved at this point and the star should simply explode. Early models hoped for something rather like that, but the real process is more difficult. The shock loses energy as it moves outward, partly because it encounters heavy nuclei and breaks them apart. It can stall rather than immediately blasting the star into space. Neutrinos produced in enormous numbers near the newly formed compact core then become essential to the modern picture. Some of their energy can be deposited behind the stalled shock, helping revive it. The precise explosion mechanism is a complicated problem involving neutrino transport, fluid motion, nuclear physics, gravity, turbulence, and the structure of the original star. Modern calculations treat the explosion as a multi-dimensional process rather than a simple spherical blast. The strong interaction matters through the nuclear equation of state, and through the properties of the dense matter forming at the centre, but even here it remains one member of a much larger physical team. A supernova is less like one force suddenly taking control, and more like nearly every difficult part of physics arriving at the same meeting. If the explosion succeeds, the outer layers of the star can be thrown into space, while a compact remnant remains behind. Depending on the mass and the details of the collapse, that remnant may become a neutron star. A neutron star is one of the clearest examples of microscopic nuclear physics controlling an astronomical object. It can contain more mass than the Sun compressed into a sphere comparable in size to a city. Ordinary atoms cannot survive under such conditions. The electrons and nuclei found in normal matter give way to increasingly neutron-rich material as the pressure grows with depth. Near the outer regions, there can still be atomic nuclei embedded in a sea of electrons. Deeper down, neutrons begin to exist outside nuclei. Farther inward, the matter approaches a more uniform state of strongly interacting nucleons. Exactly what happens in the deepest core is still uncertain, and possibilities studied by physicists include additional particles and potentially forms of matter in which quarks become more directly relevant. This uncertainty is why the equation of state of neutron star matter remains such an important research problem. The name neutron star can make the object sound simpler than it is. It would be convenient if the entire star were just a huge ball of neutrons, and we could consider the matter settled. In reality, different layers can contain different mixtures and structures. The crust begins with nuclei arranged in a dense solid framework surrounded by electrons. Deeper into the crust, increasingly neutron-rich nuclei appear, and eventually neutrons begin leaking out of them. Close to the base of the crust, competition between nuclear attraction and electrical effects may produce unusual shapes sometimes compared with familiar foods, such as sheets and strands. The comparison has inspired the informal term nuclear pasta, one of the rare situations where serious dense matter physics can make somebody hungry. Beneath this region lies the core, where separate nuclei no longer provide the best description, and matter becomes a dense mixture dominated by neutrons, along with a smaller population of other particles needed to maintain the appropriate physical balance. At these densities, the strong interaction among nucleons becomes central to determining how resistant the matter is to compression. That resistance matters because gravity in a neutron star is relentless. Each layer presses inward on the layers beneath it, and the central pressure reaches values far beyond anything encountered in ordinary materials. Quantum mechanics provides part of the resistance, because fermions such as neutrons cannot all collapse into identical quantum states. Strong interaction effects provide another crucial part, especially as particles are forced close together. At sufficiently short separations, the effective interaction among nucleons can strongly resist further compression. The balance between gravity and the properties of dense nuclear matter determines how large a neutron star can be for a given mass, and how much mass it can support before no stable neutron star configuration remains. If enough mass is added and no available pressure can resist gravity, collapse can continue toward a black hole. The maximum stable mass therefore depends on the behavior of matter at extreme density, which means it depends in part on physics rooted in the strong interaction. Different assumptions about nuclear interactions produce different neutron star structures, and this connection between nuclear forces and stellar masses has been recognized for decades. Physicists describe the compressibility of neutron star matter using the equation of state. A stiffer equation of state means the pressure rises more strongly as matter is compressed, allowing a star to resist gravity more effectively and often producing a larger radius for a given mass. A softer equation of state allows the material to compress more readily. The challenge is that conditions in the deepest neutron star cores cannot simply be reproduced in a laboratory in bulk and held still while somebody takes measurements. Nuclear experiments can constrain parts of the problem, theoretical calculations provide others, and astronomical observations add another source of evidence. Measurements of neutron star masses and radii can eliminate models that predict stars inconsistent with what nature actually produces. Gravitational waves from neutron star collisions provide additional information because the way each star deforms in the gravitational field of its companion depends on the properties of the matter inside it. The strong interaction can therefore leave a measurable signature in distortions of space, produced by objects orbiting each other hundreds of millions of light-years away. The connection is indirect, but that is often how particle physics makes itself known on cosmic scales. The deepest interior may be stranger still. As density increases, particles are packed so closely that new forms of strongly interacting matter may become energetically possible. Some theoretical descriptions allow particles containing strange quarks to appear. Others explore transitions from matter described mainly in terms of protons and neutrons to matter where quarks become a more useful set of degrees of freedom. There are also studies of quark matter in which quarks form paired states under extreme conditions. None of these possibilities should be presented as a confirmed description of every neutron star core. The actual state of matter at the highest densities remains uncertain, and current research tries to narrow the possibilities by combining nuclear theory, quantum chromodynamics, astrophysical observations, and merger simulations. Even recent work continues to investigate how a transition between hadronic matter and quark matter might affect neutron star mergers and what observable signals such a transition could produce. Neutron stars can remain isolated for immense periods, but some exist in binary systems where two compact stars orbit one another. They slowly lose orbital energy through gravitational radiation, causing the orbit to shrink until the stars finally collide. When neutron stars merge, matter that had been compressed to extraordinary density can be torn away and thrown outward. This material is extremely rich in neutrons, creating conditions where atomic nuclei can capture neutrons very rapidly. Through a sequence of neutron captures and radioactive transformations, very heavy elements can be assembled. This rapid neutron capture process is associated with the production of many heavy nuclei, and neutron star mergers are established as an important site where such nucleosynthesis occurs. The research continues on the relative contribution of different astrophysical environments to the full heavy element inventory of galaxies. Observations following a neutron star merger have provided strong evidence for the production of heavy elements in the ejected material. This means the strong interaction becomes involved in another remarkable sequence. Nuclear binding determines the behavior of neutron-rich nuclei. The merger throws enormous numbers of neutrons into an expanding cloud. Nuclei capture them, producing unstable isotopes far from the combinations commonly found on Earth. These nuclei then transform toward more stable arrangements. Some become heavy elements that may eventually drift through interstellar space and become part of later generations of stars and planets. A gold atom in an ordinary object can therefore contain a nucleus assembled through nuclear reactions associated with an event involving two objects so dense that a spoonful of their matter if it could somehow exist under ordinary conditions, would have an absurdly large mass. There's no need to imagine the strong interaction travelling outward from the merger. The strong force remains microscopic at every step. What changes is the number of microscopic nuclear events occurring and the extreme conditions in which they happen. Supernovae and neutron star mergers also remind us that the strong interaction can both bind matter and participate in environments where bound structures are repeatedly destroyed. In an ordinary nucleus, residual strong attraction contributes to long-term stability. In a collapsing stellar core, heavy nuclei can be broken apart as energy is absorbed. In expanding supernova material, nuclei can form again. In neutron-rich ejecta from a merger, unstable nuclei can be pushed into extreme compositions before radioactive processes move them back towards stability. The same underlying nuclear physics can therefore appear as binding in one environment, fragmentation in another, and rapid nuclear assembly somewhere else. The strong interaction has not changed its rules. The temperature, density, composition, and available energy have changed around it. This becomes particularly clear if we compare a neutron star with an ordinary star. In the Sun, the strong interaction matters when nuclei occasionally approach closely enough for reactions to occur. Most of the star is not at nuclear density. There is plenty of space between individual nuclei by nuclear standards. In a neutron star, gravity has removed that luxury. Matter is packed so tightly that nuclear scale interactions help determine the properties of the material continuously. The strong interaction is no longer relevant only during occasional fusion reactions. It becomes part of the basic mechanical behaviour of the star. How the matter compresses, how pressure grows, what particles appear, and what happens during a merger can all depend on strong interaction physics. And yet even a neutron star does not give the strong force complete control. Gravity is powerful because the star contains so much mass. Electromagnetism still influences charged components. The weak interaction determines important transformations and affects neutrino behaviour. Quantum statistics controls how fermions can occupy available states. General relativity is required to describe the gravitational structure accurately. The neutron star is a meeting place where physics that normally dominates at completely different scales becomes equally difficult to ignore. The strong interaction may be the strongest fundamental interaction between particles at nuclear scales, but a neutron star exists because all the relevant laws reach a balance. Sometimes that balance fails. If a stellar core is too massive, or if a neutron star gains enough additional mass through accretion or a merger, gravity can overcome every available form of support. The object may collapse into a black hole. At that point, the strength of the strong interaction cannot rescue the matter from gravity, not because gravity has suddenly become stronger between individual particles in the ordinary comparison, but because the total gravitational field of the compact object has become overwhelming. This is another useful reminder that calling something the strongest force does not mean it wins every contest. A short-range interaction can dominate inside a proton, while a weaker but long-range interaction determines the fate of an entire star. Between these outcomes lie some of the biggest unanswered questions in dense matter physics. What exactly occupies the centre of the most massive neutron stars? How rapidly does the equation of state stiffen or soften as density rises? Do hyperons appear? Does matter undergo a transition where quarks become deconfined over a larger region? Can quarks form paired phases at sufficiently high density? How do these possibilities change the way neutron stars cool, rotate, vibrate, merge, or collapse? Researchers approach these questions from several directions because no single measurement provides the full answer. Particle accelerators probe strongly interacting matter at high energies. Nuclear experiments investigate neutron-rich nuclei. Astronomers measure neutron star properties. Gravitational wave observatories listen to compact objects collide. The common thread is the attempt to understand how strong interaction physics behaves, when matter is pushed beyond the comfortable conditions found in ordinary nuclei. So the phrase strongest force in the universe becomes rather more literal in these extreme environments, not because the interaction suddenly reaches across a star, but because the microscopic properties it controls begin influencing the fate of enormous amounts of matter at once. Nuclear binding helps stars release energy. The loss of favourable nuclear fuel contributes to the instability preceding the collapse of massive stellar cores. Strongly interacting nuclear matter affects how that collapse behaves near nuclear density. The resulting neutron star may owe its size and maximum mass partly to the way the strong interaction makes dense matter resist compression. If two such stars collide, nuclear matter can be torn apart and rearranged into some of the heaviest elements found in nature. A force whose direct range is smaller than an atomic nucleus can therefore help explain sunlight, stellar death, compact stars, gravitational wave signals, and some of the material eventually incorporated into planets. Following that trail brings us back to a quieter question hidden beneath all the violence. If changing nuclear binding can release enough energy to help power stars, if dense, strong interaction matter can resist the gravity of a neutron star, and if much of the mass inside ordinary protons already comes from strong interaction energy, then the role of this force goes well beyond merely keeping particles from falling apart. It is involved in why ordinary matter has the mass it does, why stable building blocks exist at all, and why the universe contains the particular structures from which everything familiar has been assembled. That takes us away from what the strong interaction does during spectacular events, and toward the more basic question of what kind of universe could exist without it. After following the strong interaction from quarks to nuclei and then outward into stars, supernovae and neutron stars, we can finally ask the broader question that has been sitting underneath the entire discussion. What would the universe actually be like without this interaction? The answer is not simply that atoms would be a little less stable or stars would behave somewhat differently. The structure of ordinary matter would be changed at its foundation. The strong interaction is responsible for confining quarks into particles such as protons and neutrons. It provides most of the mass carried by those particles through the energy of their internal quark and gluon systems, and its residual effect allows protons and neutrons to form atomic nuclei. Remove that chain and almost everything we normally call matter loses the structures that make it recognizable. There is an important qualification though, because the title of our subject can easily suggest more than physics actually tells us. The strong interaction does not explain why the universe contains more matter than antimatter. That remains a separate major problem in cosmology and particle physics. What the strong interaction does explain is why quarks can form durable particles, why those particles have the masses they do, and why much of the matter that survived the early universe could eventually become nuclei, atoms, stars, planets, and all the ordinary material around us. It does not explain why matter won the early competition with antimatter, but once matter was present, the strong interaction became essential to determining what that matter could become. To see how fundamental that role is, we can return to the early universe, when temperatures were far too high for ordinary protons and neutrons to exist as stable, individual particles. Matter was in a much more energetic state involving quarks, antiquarks, gluons, electrons, neutrinos, photons, and other particles. Quarks were not neatly packaged into the protons and neutrons we recognise today, because the environment was too hot and energetic for those familiar hadrons to remain intact. As the universe expanded, it cooled. Once conditions dropped into the range where confinement became important, quarks and gluons reorganised into colour-neutral particles. Protons and neutrons emerged as some of the most important survivors of that transition. Confinement did not require someone to assemble 3 quarks by hand and check whether the colours matched. The strong interaction naturally allowed only the appropriate colour-neutral combinations to persist as ordinary observable particles. From that point onward, the universe contained stable or long-lived hadrons that could participate in the next stages of cosmic evolution. This was one of the first major steps toward the matter we know today. Before chemistry, before atoms, and even before atomic nuclei, the strong interaction had already determined that loose quarks would not remain loose. A proton is especially important because it appears to be extraordinarily stable. Experiments have searched for proton decay for decades, but no confirmed decay has been observed. Some theories beyond the standard model predict that protons may eventually decay over fantastically long times, but within the standard model, they are effectively stable for ordinary purposes. This stability means a proton can survive through immense stretches of cosmic history. A proton formed in the early universe can later become part of an atomic nucleus, enter a star, emerge in stellar material, become incorporated into a planet, join a molecule, and continue existing through all of those changes without its internal quarks ever becoming free. Chemistry can change what atom a proton belongs to only through nuclear processes, but the proton itself remains a recognizable, strongly bound particle. The strong interaction provides the confinement that makes this kind of durable building block possible. The universe therefore gains something extremely useful from strong interaction physics. Particles that can carry identity over enormous lengths of time. The neutron provides a slightly different example. A free neutron does not survive indefinitely. Outside a stable nucleus, it eventually transforms through the weak interaction into other particles. Inside many nuclei, however, neutrons can remain stable because the complete nuclear energy arrangement prevents that decay from being favourable. This tells us something important about matter. Stability is often a property of the whole system rather than merely a permanent characteristic of an isolated particle. A neutron that is unstable alone can become a lasting component of carbon, oxygen, calcium, iron, and many other nuclei. The residual strong force helps create those nuclear environments. Without it, neutrons could not play their familiar role as electrically neutral contributors to nuclear binding, and the possibilities for building elements would be drastically reduced. Even the proton and neutron masses themselves show how deeply the strong interaction is involved in what we call matter. It would be natural to think that the mass of a proton comes mostly from the masses of the 3 valence quarks inside it. That turns out not to be the case. The individual quark masses provide only a relatively small part of the total. Most of the proton's mass arises from the energy contained in the strongly interacting quark and gluon system. The motion of the quarks, the gluon fields, and the quantum dynamics inside the proton all contribute to the energy of the complete particle, and that energy appears as mass. The neutron follows a similar story. This means that when you weigh an ordinary object, most of the mass associated with its atomic nuclei ultimately reflects strong interaction energy rather than simply the bare masses of the quarks. The strong interaction is not merely holding together matter that would otherwise have exactly the same mass. Much of the mass of ordinary visible material emerges from the energy of the interaction itself. That fact becomes even more striking when we compare ordinary matter with the Higgs field. The Higgs mechanism gives elementary particles such as quarks their intrinsic masses, and it is common to hear simplified explanations saying that the Higgs field gives matter its mass. That is true in an important sense, but it can leave the wrong impression if applied directly to most of the mass of a person, planet, or table. The quarks inside protons and neutrons receive their intrinsic masses through interactions associated with the Higgs field, but those quark masses account for only a small fraction of the proton and neutron masses. Most of the mass in ordinary atomic nuclei comes from strong interaction dynamics. So if somebody asks what gives an ordinary object most of its mass, the answer involves quantum chromodynamics at least as much as it involves the Higgs mechanism. This is one of those details that rarely fits onto a popular science headline because it requires an extra sentence, and headlines have always been suspicious of extra sentences. Once protons and neutrons existed in the early universe, the next important step was building the first atomic nuclei. During the first minutes of cosmic history, Conditions allowed nuclear reactions to combine some protons and neutrons into light nuclei. Hydrogen remained the most abundant, while helium became the major heavier product, along with smaller amounts of other light nuclei. The residual strong interaction was central because it provided the nuclear binding needed for these combinations. The early universe could not immediately build every element on the periodic table because it was expanding and cooling rapidly, and there were important gaps in the available stable nuclear pathways. The first round of cosmic nucleosynthesis therefore left the universe chemically simple. There were plenty of ingredients for stars, but very little of the carbon, oxygen, silicon, iron, and other elements that later became important for planets and life. Gravity then gathered the gas into stars, and the strong interaction became relevant again through nuclear fusion. Stars took the simple nuclei produced in the early universe and began processing them. In stellar cores, nuclear reactions created heavier nuclei and released energy because of changes in nuclear binding. Massive stars could continue through several stages, producing increasingly heavy elements before their final collapse. Other astrophysical events, including neutron star mergers, helped create still heavier nuclei. Over many generations of stars, galaxies became enriched with elements that had not existed in meaningful quantities immediately after the early universe cooled. Carbon became available, oxygen became abundant, silicon could form rocks, iron could become part of planetary interiors and much later, biological chemistry. Calcium became available for structures such as shells and bones. The strong interaction did not decide that any of these things should be used for life, of course. It simply allowed the nuclei to exist. Chemistry and biology took advantage of what nuclear physics had made available. This gives us a useful chain from the smallest scale to the largest. Quarks are confined into protons and neutrons by the fundamental strong interaction. Protons and neutrons experience a residual strong attraction that allows many nuclei to form. Nuclear binding makes stellar fusion possible as an energy-releasing process. Stellar reactions and explosive events manufacture and distribute elements. Those elements form atoms. Electromagnetism then dominates the next level, allowing atoms to bond into molecules. Chemistry eventually produces materials complex enough for planets, oceans, atmospheres, and biological systems. The strong interaction is not directly responsible for a molecule of water holding together or a strand of genetic material maintaining its structure. Those are mainly electromagnetic and quantum chemical problems. But neither molecule would have the necessary nuclei without the earlier layer of strong interaction physics. This is a useful reminder that the importance of a fundamental interaction cannot be judged simply by how often we notice it. Electromagnetism dominates daily life because it controls chemistry, light, electronics, friction, material strength, and most of the forces we experience when objects touch. Gravity dominates the large structures of astronomy because it acts over enormous distances and accumulates with mass. The strong interaction dominates a much smaller region. Yet the smaller region is foundational. It establishes the particles and nuclei on which the larger scale behavior depends. A force can have almost no direct effect between two human-sized objects and still be essential to both objects existing. There is another reason the strong interaction matters to the persistence of matter. If quarks were not confined, the familiar division between protons, neutrons, and other hadrons would disappear. Quarks could potentially move independently over large distances, carrying exposed color charge. The entire organization of nuclear matter would change. We should be careful about imagining a universe with the strong interaction simply switched off, because changing a fundamental interaction alters many interconnected properties, and the resulting physics cannot always be predicted by casually removing one item from a list. Still, within our current understanding, ordinary protons and neutrons depend so strongly on quantum chromodynamics that a universe without the strong interaction would not contain them in their present form. Without stable protons, hydrogen as we know it would be gone. Without nuclear binding, Heavier atomic nuclei would not exist in the familiar way. The periodic table would not merely lose a few entries, its basic foundation would be missing. Even small changes to the strength of nuclear interactions could have major consequences. Nuclear stability depends on a detailed balance. The deuteron, made from one proton and one neutron, is bound only modestly compared with the energies associated with deeper quark confinement. If the effective nuclear interaction changed enough, deuterium might become unbound or its properties could shift significantly. That would alter reaction pathways important in the early universe and in stars. Carbon production in stars depends on particular nuclear energy levels, and changing nuclear forces would shift those levels. Other nuclei might become more or less stable. It is difficult to change one fundamental parameter while pretending everything else remains untouched. But the general conclusion is reliable. The structure of the chemical elements depends sensitively on nuclear physics. Our universe contains the periodic table it does, because the strong interaction has the properties it has. The strong interaction also contributes to one of the most basic facts about the world around us, which is that matter can be both stable and transformable. Protons and many nuclei are stable enough to persist for immense periods, allowing structures to accumulate rather than constantly falling apart. At the same time, nuclear reactions can occur under suitable conditions. Stars can fuse nuclei. Radioactive nuclei can decay. Heavy nuclei can split. Neutrons can be captured. Matter is not frozen permanently into its earliest form, nor is it so unstable that nothing lasts. The strong interaction participates in a middle ground, where stable building blocks exist but can still be rearranged when enough energy and the correct conditions are available. That balance is why stars can function as long-term engines rather than detonating all their nuclear fuel instantly. The electrical repulsion between positively charged nuclei makes fusion difficult, while the strong nuclear attraction becomes important only at very short range. This creates a barrier. Most nuclei in a stellar core do not immediately fuse upon encountering one another. Reactions occur at limited rates determined by temperature, density, quantum tunneling, and the relevant nuclear properties. A star can therefore release energy gradually over millions or billions of years. If the nuclear interaction acted over much longer distances, or if charged nuclei did not repel one another, stellar behavior could be radically different. The Sun's stability depends not on one interaction doing everything, but on several interactions having very different strengths and ranges. The fact that the strong interaction is short-ranged is therefore just as important as the fact that it is strong. A force that powerful with unlimited range would produce a universe unlike ours. Instead, color confinement hides the fundamental interaction inside hadrons, while the residual nuclear force extends only far enough to bind nearby nucleons. Beyond the nucleus, electromagnetism and gravity take over. Nature has a hierarchy of scales. Quantum chromodynamics dominates inside protons and neutrons. Residual nuclear forces dominate certain aspects of nuclei. Electromagnetism dominates atoms, molecules, and materials. Gravity becomes dominant for large collections of mass. The universe is not controlled everywhere by whichever interaction has the highest strength in a particle physics comparison. Each interaction becomes important under particular conditions. This is why black holes do not care that the strong interaction is called the strongest force. If enough mass is compressed into a sufficiently small region, gravity can overwhelm the pressure provided by dense matter and continue the collapse. There is no contradiction. Strong interaction. Strength refers to microscopic particle interactions, while gravitational collapse depends on the accumulated effect of enormous amounts of mass and the geometry of space and time. A neutron star can temporarily sit between these regimes, with strong interaction physics helping dense matter resist compression, while gravity pulls inward. If the star is too massive, gravity wins at the scale of the complete object. The comparison between forces always depends on the question being asked. The same caution applies to the idea that the strong force explains why there is matter at all. It explains something extremely important, but not every part of that question. Modern cosmology suggests that the early universe contained matter and antimatter processes, and observations show that the present universe is dominated by matter, rather than containing equal amounts of matter and antimatter annihilating one another. Explaining that imbalance requires physics associated with baryogenesis or related mechanisms, and the complete answer is not yet known. The strong interaction is part of the standard model environment in which quarks behave, but quantum chromodynamics by itself does not provide the accepted explanation for the observed matter-antimatter asymmetry. So when we say the strong force is beneath ordinary matter, we mean that it creates and stabilizes much of the structure and mass of the matter that exists, not that it single-handedly explains why there was a surplus of matter in the first place. That distinction makes the real achievement of the strong interaction no less impressive. Once quarks existed, it allowed them to become hadrons rather than remaining an unconfined population. It produced protons and neutrons with most of their mass, arising from strong interaction energy. It allowed residual nuclear binding to create nuclei. It made possible the energy differences used by stars. It helped determine which elements could form and which would remain stable. It became relevant again under the extreme densities of neutron stars and in the violent nuclear processes that manufacture heavy elements. At every stage, the same underlying theory keeps appearing in different forms because matter is being examined at different scales. Consider a simple carbon atom. Its electrons are responsible for most of the chemistry carbon performs. Those electrons do not experience the strong interaction, yet the nucleus contains protons and neutrons bound partly through residual strong forces. Each of those nucleons contains quarks, confined through the fundamental strong interaction. Most of the nucleon mass comes from the energy of those quark and gluon fields. The carbon nucleus may have been assembled inside a star through nuclear reactions, whose possible energies depended on strong interaction physics. The atom may later have been ejected into interstellar space, incorporated into a planet, and eventually used in a biological molecule. At the level of biology, strong interaction physics is hidden almost completely, but the carbon nucleus carries that history inside it. The same is true of oxygen in a breath, calcium in bone, iron in blood, and phosphorus in cells. Strong interaction physics does not direct biological processes, but it supplies stable nuclei with the properties chemistry uses. This separation of roles is important because it prevents us from turning a fundamental force into an explanation for everything. The strong interaction does not explain consciousness, metabolism, weather, geology, or why someone puts an empty carton back in the refrigerator. Those phenomena require their own levels of explanation. What the strong interaction does is establish some of the durable microscopic ingredients those larger systems inherit. Perhaps the most surprising lesson is how little of ordinary matter is made from the kind of mass we might originally expect. At the deepest level, a large fraction of the mass in the visible world is energy associated with fields and interactions. The proton is not a heavy container holding 3 heavy quarks. It is a strongly interacting quantum system whose total energy gives it most of its mass. The chair beneath you, the ground under the building, and the planet itself are largely made from nucleons, and those nucleons owe most of their masses to quantum chromodynamics. Something that feels completely passive, the simple heaviness of an object, is connected to one of the most active quantum systems in nature. There is also something useful in returning to the name strong force after seeing everything it includes. At the beginning, the name suggested brute strength. It sounded like a competition where gravity, electromagnetism, the weak interaction, and the strong interaction could be lined up and ranked. By now, strength is almost the least interesting feature. The real story is how the interaction behaves. It becomes weaker at extremely short distances. It becomes harder to overcome as quarks are separated. Its gluons interact with one another. It confines color charge. It creates composite particles whose masses come largely from interaction energy. it leaves behind a residual nuclear force that acts only across a tiny range. Those details matter more than simply saying it is powerful, and they explain why something so strong can remain so easy to ignore. The force hides itself by doing its job extremely well. Quarks are confined inside color-neutral hadrons, so we do not encounter exposed color charge. Protons and neutrons then form nuclei, where only the residual interaction reaches between them. At larger distances, even that fades away. By the time we arrive at atoms and molecules, electromagnetism has become the main interaction shaping visible behavior. The strong interaction remains deep inside, maintaining structures that ordinary life simply assumes will continue existing. A cup sitting on a table does not need to demonstrate nuclear stability, it simply remains a cup. The atoms in the ceramic or glass retain their nuclei. The protons retain their quarks. The quarks remain confined. None of this demands tension because failure is so rare under ordinary conditions. Stability hides complexity. Physics becomes interesting when we ask what has to be happening underneath for that stability to look effortless. That question has taken us from the atomic nucleus into quarks and gluons, through color charge and confinement, back out through residual nuclear binding, and then into stars and neutron stars where the same microscopic interaction influences objects on astronomical scales. The strongest interaction in nature turns out to be neither a distant cosmic force nor something we can feel directly. It is mostly confined to the interiors of particles and nuclei, yet those interiors provide the building blocks from which the visible universe is assembled. And if you look around the room now, nothing appears different from when we began. The walls remain where they were. Your hands still look like hands. The nearest cup has probably not become any more cooperative. But inside every proton in every one of those objects, quarks are still interacting through gluons. Color charge is still being exchanged. Confinement is still preventing those quarks from escaping, and strong interaction energy is still providing much of the mass that makes the object feel solid and substantial in the first place. So the strongest force in the universe does not need to announce itself with exploding stars, although it certainly has a role when stars become extreme. Most of the time, its achievement is much quieter and much more basic. It allows the pieces of ordinary matter to exist long enough for everything else to happen,